Hello. Are you ready for me just to go in a moment?
Yeah, yeah.
Okay.
It is 2 o'clock, so we can start normally. That's fine. So hi everyone. So we have again a full day of a few hours of PyHEP, and we're starting with Graham from NVIDIA, who will talk about CUDA number in Python. So please go ahead, Graham.
Thank you. Is my screen share working again?
Yeah, all perfect.
Okay, good. Thank you. So hi, I'm Graham Markle. I'm a software engineer at NVIDIA. where I've been for about 18 months now, and I've spent pretty much all my working time on number or related things. I also worked on number a bit in the past when I was at Anaconda between 2014 and 2016. So if you get any questions in the future or you want to talk about anything related to number and CUDA, then reach out to me anytime. So over the next 30 minutes, I'm planning to spend about 15 minutes talking about number and CUDA, then 5 to 10 minutes for a short demo, and whatever time's left over for any Q&A. So what I'm aiming to do is just to give a fairly broad and high-level introduction to number and CUDA, nothing too deep, nothing too technical, to help you start to understand what number is, who's using it, whether it makes sense to use it in your application, how to start using it, and how to get access to CUDA hardware if you need to. So, what is number? It is a compiler for Python, and it's mainly aimed at array-oriented numerical code. So it's a tool that you would use when you want to get better performance out of your Python code. And it gets better performance by taking the Python code and compiling it into native code instead of having it execute in the Python interpreter. So there's actually a whole range of things that you could do when you've got Python code and you want it to run faster. Number is just one of the options that you could look at. So for example, some of the other options that you might consider instead are to use a native library that does what you need, maybe adding some Python bindings for it if they don't exist already. You might compile your Python code with Python instead and maybe add some Python specific things to it. You might run your code under PyPy, which is another Python runtime, and that JIT compiles all of the Python language. Or you might look at using Julia instead, and I think there's some sessions on that tomorrow that I'm quite looking forward to. So number compiles Python, but it only compiles a subset of Python. It doesn't support all the language features in the entire library ecosystem. It mainly focuses on the subset that generally appears in numerical code. And we've put a lot of effort into covering as much of NumPy's API as possible. So because number doesn't support all of Python code, you have to tell it the functions that you want it to compile using the JIT decorator. So I've got a very short example in the notebook here. We'll ignore the imports and the parameters for now. The key point is that we have these functions, mandel and create fractal. These are Python functions all written in Python that we've decorated with the JIT decorator here and here. And then we can call them that function as normal.
Graham,
So,
can you just make it a little bit bigger?
Yeah, I can. Well, I can try. Let me try.
Just one or two plus should be enough.
How does that look?
Great. That's great. Thanks.
Okay. So that was the create fractal and mandel code decorated with numbers JIT decorators, just in case that was a bit hard to catch the first time around. Then beneath it, we've got some code to call the function, timing its execution. So if we call that, then hopefully in a moment, what do we see? A fractal and the execution time, which was about 0.4 seconds. So what actually happened during those 0.4 seconds? If to investigate that a bit, let's call the function again and see how long it takes this time. So for the second run, it seems to be much faster than the first time, around 0.06 seconds. And what we're seeing in this second run is how long the function is actually taking to execute. In that very first run, by the way, do you see my mouse pointer? Can I use that to indicate things?
Yeah, we can see the mouse.
Okay, cool. Yeah, so in this first run, we timed number, taking the Python function, compiling it into native code, as well as the execution. So after the first run, it's already got the native code ready to use. So the very first run always takes a bit longer than the subsequent runs. So how does this compare to the original Python code? We can call that with pyfunc. So if we do that, then what we see is that it takes a bit over half a second. So the number compiled function in this case was about 10 times faster than the Python. Typically the speedups that you'd see with number over pure Python code can be from around 10 times up to the low hundreds, sometimes 100 or 200 times. This particular example is one that I picked because it's quite easy to demonstrate number with it rather than it being a showcase of the best performance that you can get out of number. So next, let's have a look at what happened when we called that function and what number did. So we're going to do that by having a look at this diagram, if I can squeeze them both on, this diagram of numbers compilation pipeline, and then this is a very sort of high-level diagram of numbers architecture. So number actually compiles Python bytecode rather than Python source code because that's a lot easier to work with. So the first thing it does when you call a jittered function is it will use the Python bytecode compiler to get the bytecode, and then it will translate that into its own intermediate representation. It uses that intermediate representation to do something called type inference, where it will work out the type of every variable and value inside the function. And the reason it has to do that is because it eventually wants to generate native code. And that's always written in terms of specific data types and widths, so like an 8-bit integer or 64-bit floating point value. Whereas the Python source didn't have any typing in it. Python just uses duck typing, where any type of object will be accepted as long as it's got the right properties and methods. The next important stage after it's worked out all the types is the lowering stage, and that converts numbers intermediate representation into the LLVM intermediate representation. So LLVM is a compiler framework that's used to implement lots of different compilers. Which is a really useful tool because you can use it to implement a compiler targeting lots of different machines, so x86 or ARM or CUDA. And all you have to do is target or generate LLVM's intermediate representation. So really the work of number is to take Python code and turn it into LLVM IR. Then we leave it to LLVM to do lots of clever optimizations on the IR and actually generate the machine code. So once it's done that, we're at this point where we have the machine code. It puts it in the cache in case we need it again later, and it can execute it. So that was a very high level overview of what number's doing when you call a jittered function. Next, who's using number? I don't know how big the number user community is, but I like to think of it as a reasonably successful open source project that's used by a fair number of libraries. I grabbed a few metrics from GitHub and Conda and PyPI that are in the notebook. I don't know how to make too deep an interpretation of these, but I think they show that it's of interest to more than just a handful of people. I did do a quick search to find a few applications of number from different fields of endeavor. One of them, Rapids, Ben talked about yesterday, that's a fairly heavy user of number, but there's some other links on the notebook and links to more links as well. In general, number tends to be a building block of an entire software stack, maybe rather than a tool that's directly used in the top layer of the stack. Maybe some of the libraries that you're using would make use of number. So why would you choose to use number in your own code or library? I think the main compelling argument for it is that you can keep all your code as Python code, and if you like, stay within your comfort zone, or perhaps the comfort zone of your collaborators, but still get better performance out of it. Some of the other options that I talked about earlier, like Python or using native code directly, mean you end up with code in a mix of languages or paradigms. Whereas if you use number and keep all your code in Python, then it can help you to focus your efforts on developing your algorithm and implementation, instead of maybe spending more time working in a language where you need to do a bit more management of things. And you can keep using all the same tools and frameworks rather than maybe, for example, having a separate test framework for native code or something like that. So that's why you might choose to use it. Should you use it? Is it going to help speed up your particular code or application with a minimum of effort? There is a lot of nuance in the answer to that question, because there's lots of things that you can get number to do with some amount of effort. And we're always expanding its capabilities to try and support more language features and libraries and make it more extensible all the time. But the general answer is that if your code's fairly numerically oriented, and if you've got a lot of data and lots of iteration over that data, then it should be a reasonable fit for number. Things do get a little bit more complicated if you specifically decide that you want to use the parallel CPU target or the CUDA target, because you need to organize your code so that it can do lots of things in parallel. Some of the things that can be a bit more tricky to optimize with number, or things that I see as red flags when I'm deciding whether to use number, can be code that does lots of string processing or uses DICs heavily. So there is some support in number for strings and dicts, to some extent at least, but you can get a bit of a mixed bag of results with getting that code to compile or perhaps optimize well. Another thing is if your algorithms are inherently serial, then attempting to speed them up with a parallel device or parallel processing on the CPU or CUDA can be a bit problematic. But usually there's got to be some way to extract parallelism from something that's running long enough for you to think about accelerating it. It just might be that you need to rethink the way that your code's organized, or do a bit of refactoring of your code to get it that way. If your code already spends a lot of time inside native libraries that it's calling, or maybe you've rewritten portions of it with Python or a native language already, then it could be a bit of a slog to rewrite it back in Python to use with number. Finally, code that uses lots of object-oriented patterns and features doesn't necessarily translate well to using with number or perhaps CUDA. So I've mentioned CUDA a couple of times, and I haven't really explained what it is yet. So this is going to be a really quick overview of CUDA, just a very brief high-level one. The easiest way I find to think about it is first the hardware and then the software components. So the hardware is NVIDIA GPUs, and rather than going into depth about the architecture, there's basically two key points that I think you really need to understand when you're thinking about using them. The first is that GPUs tend to be a separate device from your CPU and main memory. They're connected to the system though, usually through a PCIe bus, and they've got their own onboard memory as well. So if you're going to use them, then you need to think about how you can efficiently get your data to and from them in the context of your program. The second point is that they're made up of a large number of cores that all execute in parallel on the same function. So you would literally have thousands of cores compared to the tens of cores that you might have in a big CPU. So that means you need to think about how to get each of those cores working on its own individual item of data. On the software side, because there's lots of cores, we've got to have lots of threads of execution. So typically those threads will be grouped into blocks of threads. And to a rough approximation, all the threads in a block are going to be doing the same thing at the same time on different items of data. Then you would have lots of blocks that make up the grid of blocks. Different blocks in the grid could be at different places in the function doing different things. You can have some communication between blocks as well, but you would tend not to have too much inter-block communication because that could start to become a bottleneck. So that was a little bit of an abstract presentation of the CUDA hardware and software. And we'll come back to that a little bit more in a more concrete way in the demonstration. So everybody's already got access to a CPU. There's one in your laptop, desktop, HPC node, whatever you're using. Not everybody's got an NVIDIA GPU in every machine. So if you want to start experimenting with CUDA, then there's a few different options that I'll talk about here. One Ben talked about yesterday is Google Colab. So I'm just going to quickly demo that now. You go to colab.research.google.com. So I think if I click that, hopefully that pops up. I'm just going to open this notebook that I'm using in Colab. So PyHEP 2021. With a bit of luck, I can open this. That one, I think. Now, if you want to use a GPU on Colab, you do need to go to Runtime, change Runtime type, set your hardware accelerator to be GPU. And while we're here, I'm just going to pop down to the demo section of the notebook, start off a couple of things there for us to look at before we go back to the other presentation of it. So all I'm really going to do here in a bunch of imports is import number and see what the number version is and see what GPU it's given us.
Grant, is this something that that we'd be able to do also while we're watching this talk?
Yes, I don't know what happens if loads and loads of people all try and do the exact same thing though, but you can certainly give it a try.
So the link here for Google Colab just goes to Google Colab in general.
Yes, that's correct. Yeah.
Then we have to type in the notebook link.
I think there was a GitHub tab. Let me go to that again, and then I'll just go through it a little more slowly. So if you click GitHub,
And what do we paste there? The
and then it was gmarkle/PyHEP 2021.
okay.
Uh,
This can resolve into a URL. I'd like to put the URL where everyone can see it, so they can do it in one click.
oh, okay. I mean, I could, yeah.
Okay.
It's a little difficult for me to do that because I'm not signed into anything on this machine. But are you okay?
Right. I've got it up,
Okay.
and there's a share button here.
Oh, okay.
Try copying this to Slido and see if that'll make it so that everybody can click it. Then we'll see if we bring it down. Okay. Thank you.
Okay. Are you happy for me to proceed at this point?
Oh yeah, please do. I'll try to share this.
Okay. Okay. So if you skip down to the demonstration section and the imports, then I'm going to have to go a bit fast for people to follow on, otherwise I won't keep to time. But you can sort of kind of catch up in a minute. Oh yeah, so the two things I'm interested in are the number version. On Colab you get 0.51, which is a little old now. There's we're a couple of releases on from that, but this is good enough for anything CUDA related really, certainly for getting started. Secondly, if you call CUDA.detect, it shows you what GPU you get. So Ben said yesterday you get a mix of different GPUs, or I don't know if you definitely get one or whether it's just more of a request. I've got lucky this time, I've got a Tesla T4, but you might sometimes get a K80 or a K40. So if you want to know what GPU you're using, use CUDA.detect. I also like to check what CPU I get with Colab as well. In particular, I do it in this notebook because there's also a demo part with the parallel target. So normally I get 2 Xeon cores. So yeah, import number, the number version, CUDA.detect, and then check what the CPU is. I'm just going to go back to the rest of the presentation notebook for now. So I think we've kind of gone over most of the pros and cons there. Oh, it's free. That's a pro. You can get started playing with the GPU right away if you use Colab, and you can do it with Jupyter notebooks as well. On the downside, I guess you've got limited control over the instance that you're using. You don't get the latest version of number, but that's not a problem for getting started. Maybe you won't get the GPU you wanted. And if you don't like Jupyter notebooks, maybe that would be, maybe you'd see that as a con. I don't know. It's also a pro. If you've done a bit with Colab or you want to go straight to using a GPU in your own machine to move on from that, if you do have your own GPU, then your availability is consistent. You've always got access to your own GPU. You can install or run anything on your own machine, do whatever you like with the software stack, the latest version, a number or whatever. And you can do things that would interrupt the GPU as well, like using the debugger if you want. On the downside, if you buy, although you can use any recent GPU, if you buy a low-end gaming GPU, you're going to get lower performance than, say, some pro-grade hardware like a T4 I just got on Colab. Especially if you, for 64-bit floating point, which tends to be a lot slower on the consumer devices. You'll also have to look after your own software stack. Not everybody wants that hassle. And at the moment, because of about a bunch of different conditions in the world, it's a little bit hard to get hold of high-end GPUs. So what I'd recommend if you want to get a card because Colab's not suitable, you kind of want to move on from it, is something like a 10 series GTX because they're old enough that you can get one at a reasonable cost. And most CUDA number features are going to work on it. If you get a GTX 1050, you just need a PCI slot. You don't need a giant power supply with loads of power connectors. And that's really a good enough system for doing most 95% of your development and debugging on. Once you've got everything working, you're happy with it, then you can start thinking about moving to higher performance systems later. If you're thinking about moving to a higher performance system, maybe you could use an HPC system you've already got access to. Some systems have GPUs or nodes or queues where you can get access to a GPU, along with the usual downsides that it can be hard to work interactively on some of them systems or all the usual batch job submission hassles. Alternatively, the major cloud providers offer instances with GPUs as well, which I think Ben mentioned as well. So that kind of concludes the overview of number and CUDA and getting access to a device. So what I'm going to do it. Oh, go on.
This might be a good time to look at the questions on Slido.
Oh, right. Okay.
You have the link to that?
Yeah, I had it open, but I, oops, sorry,
Yeah, if you just drag
okay.
the tab into the screen, into the window you're sharing and make it big.
I see. So the first question is, how does number handle different machines where you may not know the hardware available? For instance, between a laptop, desktop, or specialized cluster. If you write, so one way of answering that is that if you write a CUDA kernel, it's going to, as long as the GPU you're using supports the feature that you're using, which is going to be almost always the case. There's very few features that are limited to specific GPUs available in number. It will just run on any GPU. The only thing you might need to be mindful of is that some GPUs have different GPUs have different limitations on the number of threads. So you need to write your program to be aware of that. There's APIs that you can use to query to what the limitations are. If there's time left at the end, I'll go into more detail about that. The next question is, to run this notebook locally with our own GPU, we just need the CUDA toolkit. Yes. Well, as long as you've got number installed, you can use the CUDA toolkit as well. If you're using Conda, then you can run Conda install CUDA toolkit, and you will get a CUDA toolkit. That's probably the easiest way to get it. Jim's, all right, that's just the link. Another question: have you got an indication of usage of number in HEP specifically? I don't. I have to admit that the HEP field is one that I'm really relatively ignorant of. The second part of the question, are you in touch with some people to get there by chance? Perhaps I'll try to clarify that at the end. If I don't move on, then I don't think I'll get through the demo. So I'm going to flip back to Colab for the rest of the demo. And it's a very simple diffusion code. In the initial condition, we start with like a Gaussian hump of tracer, and then a finite difference kernel diffuses it over many iterations. So there's a couple of different parameters in the notebook that you can play with if you like. 20,000 iterations, and the grid is 1,000 by 1,000, which is a reasonable enough workload to make use of a GPU. So we'll set them. The next cell generates the initial conditions. I don't think it's very interesting how the initial conditions are exactly generated or what they are. The only thing I'd mention is I use numbers ngit decorator to speed up the generation of the initial conditions. So if we run that, we should get like a nice hump of tracer in the middle of the domain to start with. So first, for reference, there's the Python version, which is this smooth function. We've got a loop over the domain I and j indices, and then inside the body of the loop, we calculate the new value for this point as being some kind of average of the values of the old, previous iteration. When we run that, we run it in a loop, as many iterations as there are, and then every iteration we swap around the input and output arrays so that we don't accidentally overwrite our input. Now, I've actually got it commented out in the notebook for this demo because I think it might take too long to run. But if you want to run it, then you could uncomment this to run it. So we'll skip over that actual execution. Next, to demonstrate using numbers parallel CPU target, there's a couple of changes that we would make to that code to do that. The first is to add the ngit decorator. Secondly, if you want number to parallelize, then you have to pass it parallel equals true as well. When you pass it that, it knows that you want to parallelize, but it doesn't necessarily know how. If you write NumPy array expressions, it can automatically parallelize those. But if you're using for loops, then you have to be a bit more explicit and tell it what you want to be parallel. So here I'm parallelizing the outer loop with p-range, and then that tells number to parallelize the loop over the I index. Inside the body of the loop, the computation is exactly the same as it was before. The only thing we do when we're calling it that's different from the Python version is I'm going to make one call to the function before we start timing. And the reason for that is, as I mentioned before, the first call is going to include the compilation as well. So we just get the compilation out of the way before we start doing the timing. So if we run this, it might take a few seconds. On Colab, this issue pops up about TBB, but we're not using the TBB threading layer, and this probably won't happen on your own system anyway. It's just some old version of something. So we look, okay, we've got a slightly diffused tracer. So that was the CPU parallel implementation. Now a very quick look over a modification to that to use the CUDA target instead. So there's a few more changes that we need to make here. First is we'd use the CUDA.JIT decorator instead. Secondly, the for loop's gone. There's no for I or for j. Instead, what we do is this function would be invoked with as many threads as we had iterations of the loop. And each thread has its own I and j index. Now, each thread can use the CUDA.grid function to find out what its index is. And because we're using a 2D grid, pass 2, and then we'll get 2 indices back, I and j. It might be the case that we've got more threads than there are elements in the domain that we want to work with. So we have these checks to make sure that our particular thread is within the domain. This is just checking that we're inside an inner point in the domain. Then we use the if condition with those. If a thread happens to be outside the domain, then it'll just run this function to completion, doing nothing. If it's in the domain, then it does the exact same computation as before. There's a couple more changes when it comes to calling it. As I mentioned earlier, the GPU has a separate memory, so the best thing to do is to move the data over to the device before we start doing anything. Then we allocate some space for the next iteration as well on the GPU. We're warming up the JIT just like we did before, making one call to do the initial compile. But another thing we have to do, because we're launching with lots of threads, we need to tell how many threads we want to launch with, and that's done with this square braces syntax, what the size of the grid is and what the size of the blocks are. So I start with a slightly arbitrary choice of block size, 16 by 16, which is kind of reasonable, but kind of arbitrary for this problem. And then we need to make sure there's enough grids, blocks of that size in the grid to cover the entire domain. So we can compute the size of the grid as a function of the size of the domain and the size of the blocks. Then once we've made that call, our loop is the same as it was before, except with the kernel launch parameters as well. After the loop, we have this call to CUDA.synchronize that we need to have. And that's to make sure that the GPU is finished executing before we stop timing. So what happens when we make these calls to launch the CUDA function on the device is the CPU code can return immediately and carry on doing something. And this gets added to a queue of functions that are going to be called on the device. So you can end, if you don't have CUDA.synchronize, this loop can finish very, very fast as it tells the device to run all these kernels. And what you'd end up doing is just timing how long it takes to enqueue the kernels rather than how long it takes to run them. So if you have CUDA.synchronize, the CPU waits for the device to finish executing all its kernels before we record the end time. So if we run that, it should take a couple of seconds and hopefully we get a similar looking result to the CPU. Yep, hopefully. If we compare the results, the difference between the CPU result and the CUDA result should look pretty zero everywhere. Of course, it's always good to have a programmatic check of the correctness. So just an assert to make sure the CPU and CUDA times are close. If they are, let's see how long it took to execute. So in this case, the CUDA GPU is a few times faster than the CPU. Again, depending on what GPU you're using, what CPU you're using, what your code is like, what optimization you've done, you can get really varied results. This isn't necessarily the fastest speed that we could get with the GPU, but it's one that's easy to demonstrate. You can get lots, very sort of varied, different levels of speed up, sometimes much better than what we're seeing here. So if this all seems interesting, you want to experiment with it and learn a bit more about it, there's some links to some resources for using Number. There's a fairly comprehensive Number and CUDA course on the Number GitHub. If you want a quick intro, then there's the 5-minute guide in the documentation. There's a couple of links to learn more about how Number works. The life of a Number kernel post goes through a lot more detail of the pipeline, as does the documentation. If you specifically for CUDA, and even easier, An even easier introduction to CUDA is a simple blog post, and you can look at the programming guide for more in-depth coverage and reference. If you want to get help with Number, there's the Gitter channel. Drop in, say hi. It's good for quick questions and interactive discussion for the quick things. The discourse forum's pretty active. There's lots of helpful users in there, and it's good if you've got to share more code, links to repositories, or have more in-depth questions. Then there's the issue tracker. You can search if you're having some issues as well. Not usually your first port of call for making a question or request, but we try and keep it just for reporting bugs and feature requests. So that concludes the demo as well. I'm going to pop back to the questions and have a look.
Thank you, Graham. Thank you for the great talk. I think what we should do now is move these questions to Slack,
Okay.
Because it is time
Sure.
for the next talk. But let's go to Slack and answer them there.
Okay. Thank you for having me. Thank you for inviting me.
Absolutely. Thank you for this wonderful talk. Next is Henry about powerful packaging for scientific codes. Henry, do you have co-hosts? Excellent, yes, you do. Okay. Can you start sharing? And meanwhile, we'll move. Oh, which it's going under topic GPU, I think. In Slack?
Yeah, that's right.
Yeah, okay. Topic GPU. So that's where the discussion about the last questions on Graham's talk are going to topic GPU, and we'll follow up there.
Okay, thank you. All right, so we're going to make this just a hair bigger. We're going to be covering powerful Python packaging. And one of the first things to point out here, there are links at the top. If you missed anything that I'm saying, or we'll be moving pretty fast again. So be sure to pay attention to the links here at the top. Those are probably the most useful parts of the talk. One is a link to the PyHEP developer page. And then I have a link to my blog as well, which has lots of useful links here that you can use to find these different things again as well. Okay, so what we're going to try to answer today is we're going to be looking at how you ensure that whatever code you're using on is shareable, is usable by other people, and we're also be looking at ways to make this something that is easy to maintain long term and encourages high quality contributions. So these sorts of things really are assuming that you are not the only person using your code, and you are not the only person that will ever contribute to your code. This is not always true, in which case these things aren't as important. But we're going to assume that. So these are the topics we'll be covering today. We will be looking at environments, packages, some static checking and quality assurance, using continuous integration, distributing packages, and then we'll pull all that together into a cookie, and I'll describe what that is. And we'll look at some different systems for doing some of these things. So first thing I'd like to cover is environments. Installing globally is bad. You will break things. In fact, now that PIP 20.3, which that's a year, so that came out last year, is out, this will probably happen even more often. Last time this happened, even though I tried not to install globally, last time this broke something for me was 3 days ago, or 4 days ago, I guess now. And then this includes user installs. So whenever you see this recommended, that's bad. Whenever you see this recommended, that's horrible. Please never type that. PIP, newer versions of PIP will actually default to, if you can't install to your global location, it will install to the user location. So there's no reason to ever type this. This is the wrong thing to type if you're inside a virtual environment, whereas this is the right thing. So virtual environment, or VN or virtual env, whichever one you prefer. This is how you do it. This is something you should be doing quite often. You say python-m venv. This is available always in Python 3. In Python 2, you had to use virtual env, and in Python 3, it's still faster, and everything's kept better up to date because it's not built into the standard library, which gives you that benefit that you can update at a rate faster than Python. And this is a good name for it, but you can name these folders anything you want. And then you source or dot, you can use the dot here. And then once you're inside the virtual environment, all of the Python commands will be referring to the stuff that's inside this local folder. And then if things get old, you just delete this folder and start over again. If things break, you just delete the folder and start over again, etc. There's actually a tool called the Python Launcher for Unix that has came out very recently. This is a port of the Python Launcher for Windows, which has been around for many years in Python. It comes in the default Python installation. So if you've ever seen people recommend py instead of Python, that's the best practice for Windows. Well, you can actually do that in Linux now if you install the Python launcher. It's a separate download at the moment that may get bundled into Python eventually. And one nice feature of the Unix version is it will actually pick up this .vn folder for you. So you don't have to activate if you use py, and there's less typing to do. So py-mpip. It's also, by the way, best practice to do python-mpip, not pip itself, because pip may not be the Python that you're using. And often, though, what you're doing is you're trying to install applications. So one of the best practices for applications is to use pipx, which is pip for executables. And it's actually now part of the Python Packaging Authority. It lives next to pip in the same place that pip lives. So if you do pipx install app, then that will do all of this extra work for you, create a little virtual environment just for that application, and keep it protected from the rest of your environment. And then you can just access the executable, but the Python, you can't import from it. It will not affect your imports. Its dependencies will not affect yours. With more apps using Poetry now and having upper limits, this is going to slowly get worse and worse and worse. So if you use this, you will be isolated from that issue. That one thing may require packaging 21, and one may say that, no, I can't work with packaging 21. If they're not related, they shouldn't interfere with each other in the first place. You can even use pipx run, which will actually do all the steps in one. This is one of my favorite commands. So if you do pipx run, it will download a package named build and then call an application named build from that package. And there's a way to customize this, because you might know that the application in build is actually not called build. But you can customize this for pipx too. So build does that. And if you just say pipx run build, you're guaranteed never to get a version of build older than about a week, because every week or so it will clear out its cache. And you never have to think about what you've pre-installed. It's just there. It gives you all of PyPI right there, immediately available. So you can just run a command like that. And pipx is actually pre-installed in all GitHub Actions and Azure images. There's no Python setup command required for it. It just immediately works. It's provided as a working environment. So it's extremely useful in GitHub Actions and Azure. And it's actually also installed in the mini Linux images now by default. One of the benefits of joining the Python Packaging Authority. So you can just access that directly from any of the mini Linux images. So you immediately have all of PyPI available in a single line. These are some of the things, just looking in my last couple of weeks, of the things I've been running with pipx run. Build, Twine, CI build, monolins, Jupyter Book, bump version, last version. Let's just do a demo of last version. So I have no idea if if I've installed last version new or not. Probably not. Doesn't matter. Oops. And I've even made the same mistake before. So pipx run, and you'll see that it's been more than a week since I ran last version. So it's installing it, and there it is. The last version of CMake that's available is 3.20.5. And that will actually be a little bit faster, because then it knows where to look for CMake. Okay. CMake cookie cutter. These are some other things as well that I've also run recently, but usually there's other ways to run this. But I actually don't even know what that is. But these are other things I've run in the last couple of weeks or so with pipx as well. And occasionally it's handy. Sometimes you might quickly need to run PyUpgrade, even though you're not using the way I'll recommend doing it. And finally, there's also Conda. Conda, you can either run the Conda command, or you can install and run the Mamba command. Mamba is exactly the same as the drop-in replacement, except it's 3 or 4 times faster if you do installs, and 50 times faster or so if you do updates. And so I really recommend always using a virtual environment. I'm sorry, just an environment file. And if you use this, then it's much easier to keep things up to date. I really don't like trying to update a single package. This way you just update your dependencies here and then run conda in update, and that will update to everything you have listed in here. And it helps you track what's there. And it's also picked up by various places like MyBinder. All right, so let's take a quick look at task runners. So generally, you should be creating a new virtual environment for every project you're working on. But that's a little bit of a pain sometimes, especially if you're jumping around between projects, or if you're just contributing to a project, if you're a new contributor. It's perfectly fine if it's something you're working on every day. But if you're a fairly new contributor, you probably want something that just runs out of the box without having special setups and without having to look up things. So task runners are really useful for this. There are lots of different task runners. You're probably familiar with ones like Make. Tox was the famous one for Python, which I was rather against, but I actually rather like Nox, which is which is different. So this is what Nox looks like. We'll go ahead and just create a file. I'm just going to do a really simple little example where I'm just installing PyTest, and then I'm running the PyTest version command. Now, this is a pretty boring example, but it's something that you can kind of just see what it looks like to run it. Okay, and so you'll see that it will create a virtual environment for you. It'll tell you what tool it's using, in fact. And then it gives you every command exactly that it's running. So it helps teach you how to run this yourself if you don't want to run the task runner. Which if you're developing this daily, you probably don't, because you probably don't want to create a virtual environment every single time. And then it runs that, and then it deletes the virtual environment at the end. So this is actually really handy because it gives you a way to run arbitrary Python commands, controlling exactly what gets installed. And there's actually some options to this decorator. This happens to look a lot like PyTest. It's intentional. Use VN equals true. If I do that, it won't actually, it'll actually just reuse the virtual environment. By default, it will always install a new one and delete the old one. But you have to be a little bit careful if something gets old there. Okay. Also, this is something I run often enough that I actually have it installed through Brew now, because I just did Brew install Nox. Brew, there's really, if you're using something daily, I would recommend, if you're on a Mac, to use Brew versus PipX for installing them, if it's available in Brew. But I'm just showing you that this would work anywhere. I don't have to install Nox. Okay, and some suggestions for where to use this. And it's not installed in the mini Linux images. It's not a PyPI package, but you can simply use it via PipX, so it is available. Okay, so let's take a look at packaging, best practices in packaging. First, and probably most important here, you should always have a pyproject.toml file in your package. It will change the build system a bit. There is a process described in PEP 5.17, and in the process, it says that you either have a pyproject.toml, in which case it runs a PEP 5.17 build, or you have you don't have that, in which case it can run setup.py commands, or it can call a hook in setup tools. Most packages actually call the hook in setup tools, but you do still need to have the setup.py, just in case you run across a tool that doesn't. It's still valid. But if you do this, this will give you the modern build system. This is the direction that Python is wholeheartedly moving. If you don't like the old build system, I'm sorry. Or if you don't like the new build system, I'm sorry. It is superior in several ways, and that's the direction that we're all moving in. But it does change things a bit. So you should immediately put this file in. And if you have this file, you should always have a build system section, and you should always have this, which will make sure you get the modern setup tools build, and not the legacy one, which is some sort of weird hacked together thing that's trying to imitate the old build system. But this one should be better. So I would always target this, and it gives you a very powerful benefit. You can actually verify or require anything you want at build time, and that doesn't affect your install time requirements. So it'll create a new virtual environment when it builds. And then in that new virtual environment, it will install just these things. It'll run your setup.py in that new virtual environment. It'll create a wheel, and then it'll delete that virtual environment for you. So you're guaranteed to have this and exactly this available, which is quite nice. So if you want to use some package in your setup.py that's not installed, it's fine. And that's sort of one of the key things with moving forward with new packages that help setup tools instead of just depending on setup tools. In fact, setup tools may not be available in all the default environments anymore in the near future because of this. Okay, you should put your packages in a source structure most of the time. This is a recommendation, not necessarily a rule. And this helps you because when you run things like PyTest, if you just have that package in the local folder, it may run from there instead of running from your install. So you've lost the ability to do things in the install, such as build your package. So built packages should always be in a source folder. They actually become rather difficult to test properly. And certainly if you want to use any of the other features, automatic versions and things, then you don't ever want to be running from the local directory. Now, there are a few rare exceptions. There are occasionally times when you intentionally want to design your package to run from a local directory for some particular reason. So it's just a recommendation. It's good practice, and it will bite you occasionally if it's not in the source directory. Days since I've been last bit by that has been probably about 6. Okay, setup config is actually supported instead of setup.py, and really you should be putting anything static in your setup config and not in setup.py arguments. Just a quick aside, I will be probably not answering too many of the questions live on the Slido. We'll see if we have some time at the end, but if not, I will definitely answer every question in Slack. So please make sure that you check the Slack afterwards. I like to make sure every question has a written answer, even if I answer it as we go. Okay, so binary extensions have to be put in your setup.py. And package extras, I tend to like doing that just because I like to have self-dependency. So I like to have dev depend on test, for example. And there's no way to do that in setup.config or pyproject.toml, which is really irritating. So I tend to have them just for that. But otherwise, the setup.configs are superior, and they can be picked up by packages. There's various, and by other libraries. There's various reasons where it's nice to be able to statically analyze your package without having to build it. And you can't do that with setup.py. It's just simply, it might be impossible to parse. It may have some weird things like an error if you loaded on too new a version of Python and things like that, intentionally thrown, which makes it impossible to cleanly pull things out of it. Where setup.config is easy to read. And you can format it. In fact, the setup.config format actually will fix some common mistakes and things too. So there's lots of really nice features with having a static configuration, and you can mix and match. So just put as much as you can in setup.config. It also helps you avoid having helper files in your setup.py, because now your setup.py is only the logic. It's only the build logic. It doesn't have the name of your package and all this sort of static stuff. I also recommend using extras. And so, for example, if you support tests, which you should, then have a test extra. And that way you can install your package with a bracket test, and that will install all of the test extras. So these are some recommendations for names for common extras. Okay. Do not ever forget Python requires, possibly the most important line in your setup.config or setup.py, if you really feel like you have to have it there, is your Python requires line. You should always have that regardless of what your Python versions are. The reason is that this affects you from the last release instead of affecting you from the current release. If I suddenly realize, if I make a release and say I drop Python 2, and I suddenly realize I don't have Python requires, it's too late. I can't fix it. People are no longer going to be able to even install my package on Python 2. I have to go back and yank the release and do a new release or do something like that to fix the Python requires. So this should be the first thing you fix if you don't have it. We'll move forward because I have other things I want to cover, but feel free to read this as it describes describes how PIP handles this. Also, don't put an upper limit on this. It wasn't designed for that. It doesn't work correctly. So, but it's perfect for limiting and removing lower versions. So static checking, I highly recommend you use pre-commit. In fact, I recommend it so much, I'm not going to show you pipx run pre-commit. I will assume that that's such a standard feature. You should always be installing it somewhere. And this allows you to run any possible check. It's basically a task runner, but designed specifically around the idea of checking code. And it's designed really around the idea of doing fast checks. Usually you don't put tests here. But one example of one that I'll show you is MyPy. There's two ways of running it. You can do a pre-commit run, which will check only what's changed in your Git staging area, or pre-commit run -a, which will check all your files. So when I'm running it by hand, I usually run this. If you run pre-commit install, it will actually run every time you commit, which is sort of the recommended mode, the pre-commit. I install it some of the time. I run it this way a lot, most of the time, even if I haven't installed. There's lots of great things here. I would really go to this page and read about all the different checks and things that you can put. And there's actually a service, precommit.ci, which is a specialized CI service. It also has its own GitHub action. But the service will actually give you weekly, or you can configure that, updates to all your pre-commit hashes. These things have to be pinned exactly. That's how pre-commit caches itself. So don't ever put master or main or whatever there. And then you can use pre-commit auto update to update all of them. And any modifying checks will be committed directly to the PR. So if somebody commits something and they didn't appease Black, Black will change it in pre-commit. Pre-commit CI will commit it, and then they don't. Your committer doesn't even have to worry about it. There's no back and forth. Hey, please fix my style. Please run this. Please do this. It just happens. It's done. Non-modifying checks then are still just a failure. And this actually globally caches all the environments, so it's extremely fast, running in just a few seconds. So here's an example of a more detailed check. Here's MyPy. Give it a specific one. Then we can even tell it what files. If it doesn't change files there, it doesn't run the pre-commit. It doesn't run pre-commit on it. We can tell it what arguments. It has some. This hook has some default arguments. You can look that up really easily by looking at that repository. But we just turn them off by just having empty, and then you can list the dependencies to put in this virtual environment. Every single one of these will get its own individual virtual environment in whatever system it is. If you have Ruby, it'll get a Ruby environment. In Python, it'll get a virtual env. And you control exactly what versions and everything go in there, which is very important for MyPy. So often this is the only recommended way to run MyPy for me. All right, so you should always have CI. Just to show you that CI is actually really easy to set up. Here's a actually rather long job. See, it almost even fills up my whole screen. You tell it when to run. This is an example of a linting job. So this would be optional especially if you run precommit.ci, you don't need this part. And this is running your tests on several different versions of Python. This is using Nox and pipx. So I set up Nox here. And then with pipx, I run, and then it's pulling out different Python versions from here, because pipx will run on the default Python version, which is 3.8, I think. Okay. But you can easily do other ones. There's a different one on the scikit website. Just wanted to show you a slightly different example there. But that's it. Now you have even multiple runs. Okay. So then this has lots of great features, including you can upload artifacts and then download them from the UI. So if you want to build a PDF of your paper there, or web pages or whatever that's usable, it's not just continuous testing. It can be continuous anything. Actions are extremely easy to define yourself, either locally or in a repo. You can just use the shell if you want. It's really, really, really nice. And then you can even use Dependabot to keep your actions pinned, but updating regularly, since pinning is nice, and you can even do different pins there. All right, so for distributing packages, I recommend using build if you're building SDIS or wheels for pure Python packages, or SDIS if you're doing anything else. And that's really the nicest way to run it. And then for building anything else, I recommend CI build wheel, which has been extremely powerful for building different things. So this is just an example of all you need to do. And this is actually building every known wheel for every common platform. This is a normally something that you would spend roughly 400 lines of CI code to do. So, and you can configure it through these. And in fact, there's an upcoming feature in 2.0. In fact, I recommend using the 2.0.0 alpha 4 for everything, just because this is so useful. There you can drop it in your pyproject.toml file. And in this case, it's really easy to run it locally. You can just say pipx run. In this case, right now, you have to pin, obviously, an alpha version to get it. And then tell it to produce Linux wheels, because you don't want to run this locally for macOS or Windows wheels, because it installs things globally at the moment. But you can run it just fine for local, and you can build your wheels this way locally, your Linux wheels, your mini Linux wheels. It's really handy. And then Conda Forge is a way to build Conda packages. Okay, let's just take a quick look at Cookie Cutter to create. To basically do everything I just said. I can, because I didn't copy that. I can do this. Yeah, I didn't. I can do all of this at once. Let's try to do a live demo of that. Okay, sure, it's fine to download it or rerun it. I'm just going to call it package is fine. It'll default to scikit-hep, but you're welcome to use this for anything else that you want. Put in a name there. Let's do a FLIT 621 package, because that's going to be fun. You can pick different kinds of packages, fill in the rest of the information here. You can actually default some of this information if you want using Cookie Cutter. And there we go. So if you look, we now have a example package here, and it's a FLIT package. So it actually only has a pyproject.toml. So if I just look at that file, pyproject.toml, then there you go. That's the entire package. Oops, this is the wrong one. Sorry, there you are. It has all the setup that I've done. And then if I do that, again, it only has a pyproject.toml, and there you go. So that's what it looks like. It's got all of this configuration set up, and everything is set up in the pyproject.toml file. So this is really handy. You can even do binary packages using PyBind 11. That was an option. So there are alternative packaging systems. You just saw one. This is actually using PEP 621, which describes a way to describe a general configuration for all package backends, which is supported by 3 right now. Setup tools hopefully will support this soon, but you can just describe this, and then it doesn't matter which backend. In fact, I can just change this statement here to using trampolim, or which is trampoline in Portuguese, or way, and this will just work because it's the same configuration. It's a general configuration format. Very nice. I have played around with poetry. I sort of am a little worried about recommending it wholeheartedly. It sort of combines all of these things together, but it makes several rather bad decisions, especially for libraries out of the box, and you have to know to change those and not go with its sort of recommendations if you use it. And it's a little slow to update on some things too, like getting proper Mac support. Last thing I want to point out, scikit build. This is actually having is actually something that builds extensions using CMake. So it's a really exciting thing for us. It has a fairly significant user base. It supports all different, variety of different things. And of course, it's using CMake. One of the best things to come out of this is this CMake and Ninja.
Well, Henry?
Yes?
Sorry that I have to do this, but yeah, you're running out of time, and there are quite a few questions. So actually, technically you have 1 minute left. Oh, no, 0 minutes left. So can you try picking one question from Slido, answering it, and then we'll do all the rest on Slack?
Okay, so the only one that's been voted up twice has been this is the correct way to install packages to set up a new virtual environment for every project you're working on. I would say yes, unless you're using one of these other techniques like the task runners. Every project usually should have its own virtual environment. There's absolutely no reason one project's environment should be messing with another project. So I always have a .vn folder and sometimes multiple folders inside each project. So it doesn't mean you absolutely have to do that. And if you're using Conda environments, you might be tempted to reuse the same name. I'm actually running this notebook from the Level Up Your Python environment just because those are named environments. But I actually did create an environment, or I have an environment file for it. Okay, I will be answering questions on Slack. So please read the statement here about scikit build.
Great. Okay, thank you very much, Henry. Okay, so reminder everybody, check on Slack for more questions and answers about Henry's talk. And meanwhile, we will go to Irina, who will be talking about active learning for level set estimation. So Irina, are you? Yes.
Hi. Yeah.
Great.
Here, I'm going to share my screen.
Okay. A little bit closer to the mic could help. We need more volume. You need to be louder.
No.
Okay.
Okay. So I'm running this from my local machine, but then in Indico you can find the link to Binder and to the repository. I should say that because we are going to do a bit of intensive computation in Binder, it's going to take a while. So there might be a point where you can't follow the talk because it's still running. But you can check that offline. Okay, so I'm going to talk about active learning for level set estimation of black box functions. And I'm going to give 2 cents about what the logic of the algorithm is like. But this tutorial is more about how to use the package that we constructed to implement this type of algorithms. So this is work done by my colleagues, Lucas, Gilles, Patrick, and Kyle, and also supported by several funding agencies. One of them is PyHEP, who is also sponsoring this edition of PyHEP. Okay, so what is the motivation for Excursion? Our motivation is based on this plot. This is the typical exclusion plot, the end step of a high energy physics experimental analysis. And it's the plot that will conclude which areas of the parameter space of a new physics theory are excluded versus which ones are not. It's very expensive to produce because evaluating each of these points takes days or even weeks. So that's why we want to use our computational time smartly, and we want to query this simulator, these black box functions, which I will explain more about it later, as few times as possible. So the idea is that instead of using a regular grid, we just evaluate at the points that are important around the contour, and some more exploration. This has the advantage, and this is what it is implemented in Excursion. This has the advantage that we can control the granularity of the estimation of the contour of the level set, because we can have a finer grid than with the current approach, and we use active learning and Gaussian processes with GPyTorch support in this library to make this possible. Okay, so that was the real world motivation. And here I have an image of a 3D function in red. And there's a threshold in blue. And then the contours that this threshold makes in the function are above. So we are interested in finding these silhouettes, the level sets. And imagine in the high energy physics example that this surface is a CLS surface or p-value surface. And the domain is the parameter space of a new physics theory. So we are interested in finding what is the border that will separate between excluded parameter space and non-excluded parameter space. And also, by not evaluating the whole grid, we can also scale up in more dimension than just 2, because we are not evaluating the whole grid. This is the setting, and here we have a more formal description of the problem. We basically will have a black box function, and that is a scalar, and we want to find the set where the function takes a certain value. Okay. And because querying a real black box function is very expensive and we wouldn't be able to do it in a tutorial, we have generated some fake black box functions, and that's what we will use here today. The method consists on starting with an initialization data set, and then we train a Gaussian process over this initialization. And we use the Gaussian process as a surrogate model to interpolate between the samples of the true function that we have. Then we will calculate an acquisition function for all of the domain, which is very cheap. And this acquisition function is the same as how worth it is to evaluate that point through the expensive pipeline. So the one that has the maximum accuracy, sorry, the maximum acquisition function will be the one that we select. Okay, if you haven't fully understood the method, that's okay, because we were going to see it along with the code. This might remind you of Bayesian optimization, but our problem is a little bit more difficult because we are interested in finding curves and not just points. And these curves could be, they could be non-connexed, for instance. We have inspired our library in other libraries that that exist for Bayesian optimization, which are scikit-optimize and Botorch. We're actually working on a Botorch implementation. And we are also using GPyTorch, which has fast state-of-the-art posterior techniques. It's based on Torch. Okay, so let's get started. We are going to use, we have two tracks in here, the casual user and the advanced user. And what is a black box function? Does it keep track of something? In the Slido, black box functions simply mean that we don't have a formula for the function. It means that it's for instance, the outcome of a simulation. You query a simulation with a certain set of parameters and you obtain numbers, and you don't know, you don't have an f of x equals a formula. That's what black box function means. So we are going to load a predefined test case in 1D out of the box. And this is the test case that we are going to consider. The dashed line is the true function. The gray line is the threshold. And we want to find the red stars, the points where the threshold meets the function. But without knowing where this dotted function is a priori. Okay. Now, once we have loaded a test case, we need to specify the Gaussian process. So if you're not familiar with Gaussian processes, well, it's okay. Just for now, know that depending on our different choices that we make about the Gaussian process, we will have different behaviors. So you need to make some choice. But if you're a casual user, don't worry about it, because we have out of the box setting for you, several of them, and in the form of a YAML file. So here we have a YAML file that I'm loading. This algorithm specs, oops, sorry. Let me show you. That has the example that we're going to run, how many initializations you want to start with, the updates, and then all of the settings for the Gaussian process, that you don't have to worry about it. And after that, I will explain what the advanced users should do. Okay, so we have loaded the specifications, and now our package is agnostic, is device agnostic, because we often need to use a GPU. We are going to initialize a GP, and this is going to initialize a GP with the options that we have loaded here. Okay, and we are going to plot this initialization. This is random, so we can run it as many times as we want, and we get different. Okay, so in here, the blue lines and the blue shadows refer to the Gaussian process, which is going to be our estimation of the true function. And we have started with 2 initializations. And now we would like to start running the method that I have described before, the acquisition function and so on, to try, to try to find the level set. Okay, this is for the advanced user, so that's why it's in a string. The 2 initializations define the prior. No, the 2 initializations are giving you a posterior, are giving you something to start with instead of starting out of nothing. So the advanced user should build a class like this one, which is the GP model. And this is in the same way that PyTorch, GPyTorch does it. And the advanced user should specify a mean and covariance and a forward one, and a forward mode, which is always takes this shape, as long as you have specified the mean and the covariance. And then the advanced user should also initialize the likelihood that they want. And I have put links above to the GPyTorch documentation where you can see how many likelihoods you can initialize. Then you should initialize the model with training data. Train the model manually, because again, you're an advanced user, so you'd want to have full control of the moving ingredients of this algorithm. And then you would initialize the estimator, and we are in the same page now with respect to the casual user. Okay, this is just for reference, so don't worry if you are overwhelmed. Okay, we are initializing our estimator, and this estimator is going to keep track of what is the next point that we are selecting in order to find the level set. And the several methods that it has go around this, the logic of this algorithm. It's going to update posteriors, etc. You will see now. Okay, now we're going to start the active learning loop, now that we have everything loaded. And this is just for saving the plots and the diagnostic files that we'll get along, which are quite a bit. We're going to run this this loop. Okay, I'm going to run it first because it will take a while. And after that, and meanwhile, I will explain what it does. So here, I want to iterate this algorithm, the active learning algorithm, a number of times. Estimator step finds the next point that you need to evaluate to in order to find the next point that you need to evaluate in order to find the level set faster. This step is plotting the update. So the Gaussian process with this new data point updated. And after that, okay, update the posterior, and we get diagnostics, and at the end we print. Okay, so for instance, in here, you can see that the first iteration selected the point 0.49, the second one, the 0.29, etc., etc., etc. And then we are going to visualize this better with a widget. This is the performance. Accuracy 1 means it has founded the level set. You can play with that later. And here is the widget. So we see that this is the acquisition function in orange. So this is the maximum one. So this is the point that we should evaluate next. And then the iteration, it does exactly that. It goes to that point and evaluates. And then everything gets updated. And we do it over and over. It's going to find more points. And at the end, it has basically founded the level set that we wanted. And as a consequence, it has also modeled very well the function, but this is not always the case. And now the acquisition function is just 0 because there's no uncertainty anywhere, and it will just start picking points in order. Okay, let's do a tweak to this first example. We're going to add noise. What happens if our black box function if our black box function is a noisy observation? If we have instrumental noise, for instance, well, we would have to add this epsilon, which in this case for the tutorial is going to be a Gaussian, a normalized Gaussian. And I'm going to repeat the exact same code that I posted before, but a bit more compact because we have seen how it works. You see that this time with noise, the evaluations are not exactly in the black box function. It's in another one. It's a bit off because there's instrumental error. We're going to run the active learning loop. And this might take a while. You can see here, this is my local computer, my local environment with the virtual environment, like we saw in the talk before mine. And here there are many files that are generated by just running these loops. Like you can keep track of all of the images in between, diagnostics, etc. So you're going to see this number increasing. Okay, for a noisy black box function, this is going to take a while more than before because the noise prevents from making a good estimation of the level set with few iterations. So we are going to wait a little bit, and I'm going to answer questions in Slido. What is the prior in that case? Okay, so the prior, what I mean by prior is a prior over the space of functions, which is what a Gaussian process is. And a Gaussian process, you need to make some choices. You need to make the choice of a kernel and the choice of a mean. The mean typically is put at 0, and that's not like something that you have to care about much, but you have to care about the kernel. And there are different types of kernels that you can use, and that's what I mean by prior. These choices that you make about the surrogate model before the data comes in. All right. Let's see. Because this is a bit of a computationally intensive tutorial, would it be okay if I take longer, but I go and ask questions on the go while this is running?
Oh yeah, please do.
Okay, so there's another question in Slido that says, GP is a prior, not a kernel. Okay, a GP, yes, a GP is a prior over the space of functions, and it has a kernel. A GP is not the same as a kernel. It's one of the components of a GP. This is taking a bit long.
It could help if, so for answering questions, it could help if you move the tab onto what you share so that we can read the question as you're
Sorry. Is good? Thank you.
Mm-hmm.
Perfect. Now it's better to visualize this with a widget. So let's see what the iterations were doing. And the same, we have the acquisition function here. So it's going to take as next point the maximum of the acquisition function. And at the end, basically what we want to see is that this took many more iterations because the noise makes it very difficult to get the level set correct. But what I want you to appreciate from this picture is that all of these gray lines are the evaluations to the expensive black box function, which in our case is just generated data. And the algorithm is concentrating them along the points that really contain the level set that we are trying to find. And it's not querying the function at the points that there is no level set. So in here, 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 and here. But because of the noise, we're really never going to get it a pinpoint estimation. Okay, so this would still be faster than evaluating with this level of coarseness, but along the 1D grid. This is the end of the 1D tutorial, and with this, I'm going to show an example of a 2D tutorial. So we also support multiple functions. So we want to estimate the level sets of multiple functions, but at the same time with the same queries. And this is what you have here. They look very similar because for convergence purposes, I made them similar so that we don't stay until tomorrow here. But they are different functions. The one is slightly scaled up. And they also have different level sets. So we want to make the same evaluations. We want to query the same X and Y points. You see that the red dots are always in the same. Let me put it. Okay, the red dots are always in the same position in both of them. And here you have the acquisition function. So in here, this is basically the more purple an area is, the more worth it is to evaluate at that point in order to find the level set of this and this function. This is a GIF that I have made with a loop similar to the ones that we had before, but we are also going to run a 2D example here with batches. So by batches, I'm going to start running this. By batches, what I mean is that so far we have only evaluated one point at a time, one red dot at a time, but it would be faster if we could evaluate a batch of points at a time and then parallelize each of those points in the case that we are, for instance, querying a simulator at CERN. And the structure of this example is exactly the same as the ones before. I'm evaluating this active learning loop, and then we will see the result in a widget. And sorry, I don't have any pre-evaluated images, so we'll have to wait to see. To see the results of the batches. I'm running this on a CPU. So now you see why is it important to have a device agnostic package if you're based on if you're going to be based on torch, because quite easily you're going to need a GPU. See that the number of just by running these toy examples, the number of files it's quite big because we want to keep this is expensive computation. So once we run them, we don't want to lose the information. I want it to be stored somewhere that I can check it after. That's why we made it verbose. One of the things that you can check is, for instance, the confusion matrix along the iterations. This is the confusion matrix from classification. So if we classify points below or above the threshold, and if we incorrectly classify with our estimation, we incorrectly classify some of the points, then we will have a confusion matrix. Like in the same case that we will have a confusion matrix from classifying cats and dogs, but interchange cats and dogs with above and below the threshold. This is one of the other outputs from the package. And please ask your questions in Slido so I can answer them while we wait.
And just as a reminder, you have 5 minutes left in this talk.
Okay, thank you.
But it's true, I don't see any questions on Slido right now, so but now is the great time to ask them, everybody.
Yeah.
While stuff is compiling or running, is always a good time to sneak
Yeah.
in.
Okay, done. So we are going to visualize it in a widget, which is going to be better. Oops, it's a bit small. It's a bit too small. Well, there are 3 dots at a time instead of 1. And then let's see if the solid line matches the dashed line at the end. And it does. And it does it, if you remember the other one, it does it faster at the 12th iteration because we are taking 3 points at each time and not only 1. So it will converge faster. Now I have a 4D example here, which I'm not going to evaluate. I have pre-evaluated it, but it's in Binder, so if you have the patience, you can do it. And in this 4D example, our true function is going to be a paraboloid, and we want to find the level set at t equals 1. So when this is all 1, and this corresponds to a 3 sphere with radii 1. So if we do the same thing, the same loop, we should find this 3 sphere with radii 1. And the way I'm going to show you is that, okay, this is evaluated. And at the end, I plotted a histogram with the norm of the selected points. So the threshold is at norm exactly 1, because it's the 3D sphere. And we have no way to visualize this as the way that we've done before. So I thought that this histogram would be nice. And this is the norm of the selected points, the points selected by the algorithm. And you see that there's a lot of concentration around 1, which is good because we want the algorithm to not waste time looking around the space, but to concentrate around the contour that we want to find. And then it does some exploration below and above, which is also good. Okay, further work here. We are working with an PyHEP fellow on improving the code, and we are going to develop multi-resolution support in the near future because of the type of research that we are doing with the exotics group at Atlas. And we're also very interested in including the possibility of querying a black box function that is external to the code in the similar way that we've seen in some other PyHEP talks here. And for instance, high energy physics simulators. That's it. Thank you for having me, and I will answer some of the Slido questions very quick. Okay, F-score of this algorithm. F-score of this algorithm, I'm not sure what this means. Can you remind me again, why do we want to have the levels, not extrema? Oh yeah, we want to have levels, not extrema, because we are motivated by high energy physics examples. And in high energy physics, we want to find the levels at the contour set at a given confidence level so that we have an exclusion area and versus a non-excluded area for the parameter space. What kind of Bayesian optimization is using parallelization when sampling points to evaluate? How are the points chosen with acquisition function? So this is a bit, so on one hand, you have Bayesian optimization, and on another hand, what you could do if you are getting batches, using batches of points, is to parallelize those batches, and then wait for the results of these batches into your cluster, and then feed them again to the algorithm and update and start again. So it's not a kind of Bayesian optimization that uses parallelization. It's two separate things that we can combine together. And for the F-score of this algorithm, I'm happy to respond this on Slack because maybe now I don't remember what an F-score is. And I'm happy to answer that there.
That would be great because it's time.
Okay.
Okay. Thank you.
Thank you.
Okay. Next, we have sir. Please help me with your name. Actually, Serdba. Talking about Gallifrey, a modeling technique for black hole images. So, are you there? Let's see. Actually, I'm trying to find you in the list of participants. Oh, there you are. Okay, so I've made you a host.
Sorry about that.
Yeah, great.
Yeah, it's sort of basically.
Yeah. Let's see. I don't see you yet. Can you share your screen?
Yeah. Can you share my screen now?
Perfect. Yes, we can see it, and you're all good. All right.
Oh,
so,
great.
10 minutes.
So, a very good evening to everyone present here. My name is Saurabh, and I basically I recently graduated my bachelor's degree last November, and I'm actually working into this particular field, which is testing general relativity using black hole images and with the Event Horizon Telescope. So I'm working on this project, which is basically testing out different modified gravities and mainly general relativity using theory agnostic approach. And in the process of doing that, we actually created a library, a Python library, which is called Gallifrey, a small reference to Doctor Who, if anyone is aware of that. So given a small reference to that particular scientific show, sci-fi show. So Gallifrey is basically a geometric modeling and parameter estimation framework, which we have developed using black hole images, which we'll receive using a very long baseline interferometry or VLBI, and do the parameter estimation using Bayesian techniques, which we have been doing all these days in the workshop itself. So basically, as we know that last year we had, in 2019, we have some amazing phenomenal results by Event Horizon Telescope, which provided us with this image of M87. So we are going to look into similar aspects of that as to how to do the simple parameter estimation in the framework of general relativity and relativistic realm in which we are working with black hole images. So the outline of this talk is quite simple. So first 5 minutes, I'll be talking, or let's say 3 minutes, I'll be talking about basic, the motivation as to why exactly are we doing this, the whole theoretical background, and creating all those amazing black hole images. And the next part, I'm going to explain the basic library that we have created, which is Gallifrey, totally based on Python, and how we can actually use it and how we are using it to work out different theories right now. And it's still in development stage. So just to give a brief outline, in 1915, we had general relativity while with Einstein. 1916, we had the very first solution of a black hole, which is Schwarzschild black hole. In 63, we had this Kerr black hole, which is a rotating version of the Schwarzschild black hole, which has some angular momentum. So what we had is we had a generalized solution in 65, where there is a charge and an angular momentum of a black hole. And this particular black hole is shown using this simple result, which is called a space-time interval, which is given by this particular Kerr metric, as we say, where the temporal components are given something like this, and similarly with other components like these. So here we have the space-time Kerr metric, and there's this Noether theorem, which we say is through the properties by which a black hole can be characterized as just its mass, angular momentum, and charge. So these are the three properties that we have normally to characterize any particular property of a black hole. So we're gonna actually, so the basic thing is to actually test Noether theorem as to if we have any other properties which can determine any other aspect of this particular black hole. So to test our theory, what we have is we need to have a generalized solution of this particular black hole that we already have. Now, to have such a solution, we need to have a theory agnostic approach, which means that the theory should remain itself as in general relativity. That means that we are not doing some modifications of Lagrangian in the theory. So we just need to have a simplified version of GR. But in that GR, the space-time is actually parameterized, which means that we are having some higher order and lower order terms in order to have some extra terms which would deviate from the normal solution. So here we can see that we have this particular space-time, which is said as KRZ solution, in which we have these terms such as A, W, and D and B and A. So the A, B, and W and K, these are some of the terms which are interdependent on mass and angular momentum of that particular black hole. And then there are some different, extra deformation parameters, as we say, such as like A01, A02, A03, and so on, so on. And similarly, we have terms in W1 and W2 and so on. So these extra deformation parameters, when set to 0, we recover the original solution as the Kerr metric. So that's why we need to have a generalized solution when we are trying to test our theory with the observational data set. And if those extra deformation parameters, somehow, turn out to be 0, then we can say that general relativity is still holding that. So the main motivation behind all these things is to basically find constraints on those deformation parameters and see if we have some deviation from recent results or not. And to check these things, we use the basic equation that we normally use in all the numerical routines that we have is the geodesic equation, which is given by this not so simple yet a bit complicated equation, which is a four-dimensional equation in which we have, left hand side we have the four acceleration sort of a thing, and right hand side is the Christoffel symbol, which is dependent on these metric terms, these components of dt, dt phi, dr, d theta, and d phi square. So these are the basic terms that we have, which are dependent, and we solve these equations backwards in time, which we have a numerical routine that I'll be explaining later. And this is the main equation that we use to basically solve the path of light and explain the basic phenomena, which is the shadow phenomena, which I'll explain in the next slide. So the main motivation behind doing all this thing is basically to generate black hole shadow images. So if you see an image which is right here, this is the M87 image of a supermassive black hole, or let's say supermassive compact object at the center of the M87 galaxy. Here we see that we have a small dark region. So this dark region is actually regarded as the shadow region, which means that the path of light is actually just there. It's not able to escape out to the observer at Earth or at infinity, and hence we are getting a dark area. So what we are doing is basically we generate these theoretical images as to compare it with our theories in general relativity and see if we have any deviation. And in order to do so, we have different model of accretion regions of this of the surrounding accreting matter. So for this, we have an example model, which is a geometrically thick disk, where we have the intensity, which is given by this particular expression, in which G is the redshift factor, J nu E is the emissivity at some particular frequency, and dl prop is the proportional length. So we use some sort of accretion matter around this particular black hole, which will lit up the surrounding area and give us an effect of something like this image. And we generate those images, and then we try to use our existing theories to test out our own version of hypotheses. So here we have this geometrically thick version in which the accretion matter has a structure of like this, where there is some thickness at the starting, which is quite low, which is thin region, and then it expands linearly. So we have this kind of example as a model for the first task. And what exactly we do is we actually try to trace back the path of the photon from the starting region, which we have the image plane of the observer far away from the particular source, which is black hole, and the far away observer is at Earth. So we consider a sort of a screen, and in simple terms and in computational terms, when we say screen, we have a particular grid sort of a thing in which we fire photons from that particular grid, and that particular photons travel back in time, because basically we have photons coming from source to us. But here we are actually firing it away, and which is much more computationally inexpensive compared to forward ray tracing, which is coming from the source. So because then we'll have to fire a lot of data points and hence a lot of photons. So here we use numerical algorithm, which is the backward ray tracing, to trace photon backwards in time from the observer where we have on Earth, and see where those photons trace back to the emission point in that particular accretion region. And we then try to image this thing. I won't be taking much time into explaining this, but shadow emergence for phenomena, but I'll just be dwelling into the aspects as to we have the shadow image and then how we proceed further into explaining these things. So here are some sample images that we have generated using the simple thick accretion disk phenomena. So here what we have is a rotating black hole in its extremal, where the spin is in the first row is 0, which means the black hole is not rotating at all. And in the second row, we have a spin, which is 0.99, which is the extremum case, in which it is a very fast rotating black hole. And the region is quite thick. And that's why we have images something like these, in where we have the inclination around 8 degrees. We are watching it around 8 degrees from the equatorial plane. And then when we are watching it on the equatorial plane, then the images are something like this, which is around at 90 degrees. So here we have a small, we'll say as a photon ring. I don't know if you can see here. Let me just zoom it maybe. So here we have a photon ring, which is the main essence of this whole thing, which explains that there is multiple images of that particular photon, which is winding up infinite times and then coming back to the observer, which gives us another interesting phenomena of gravitational lensing.
So this is super cool, but I think you have just 1 minute left.
Okay, so sorry about that. Oh, yeah. Okay. So next, coming to the library, what we have is the Gallifrey library. So what we do is we actually model these black hole images in two particular forms. First, we have the geometric form, and then we have general relativistic form. The general relativistic form, I explained it in the previous slides. The geometric form is simple, simple forms which were told in previous talks as well, where you generate simple images such as a disk or crescent-like image. So those are geometric models, and we extract the basic parameters of that image, such as the disk width, disk radius, the total flux intensity, and all those other parameters. And we use Bayesian formalism to actually extract this particular phenomenon. So I guess maybe I can just skip this thing and just came to the main essence. So this is an example of a geometric model where we have two disks subtracted or different radii of different diameter from each other, and then it is lit up. And so here's a simple example of this crescent model, which was proposed in 2013. So we have these different models already implemented into our library, where we have Gaussians and some advanced level models such as excess ring and excess Gauss, which can actually mimic the properties of accretion, yet not in a very ideal way, but still they can somehow have some similar effects. And this is a simple version as to how one can simply create a simple model, is simply setting up the parameters of this library and initiating with this image object we have in the models module, and then simply calling it with the sky map so that they can able to generate a two-dimensional array and present a particular 2D map of the intensity. Although this is a bit of computational expensive, we haven't yet optimized it according to our conditions, but we are still working on this thing. And we can simply also blur it using some scattering kernels, such as of the Sagittarius A star or interstellar medium. So right now we have here mimicking an effect of Sagittarius A star kernel. So we can also find the visibility amplitudes of this particular image, which is simply Fourier transforming that previous slide, the previous image, and receiving how we can see it with a radio telescope under ideal conditions. So we have some simple commands to do that, and we have tutorials which are already uploaded on GitHub so that one can simply create those images. So for model fitting this particular library, this is the likelihood that we normally use, which is a form of a Rice distribution. And it is a generalized version of Gaussian distribution, where once we have signal to noise ratio very high, it becomes back to the Gaussian. So the quantity that we normally fit is visibility amplitude. We can fit all these quantities as well, which is closure and closure phases, which are all irradioastronomical quantities that we can use. And we did our best fits with these geometric models to this MET7 image, and we have found some good results which are matching with the original papers of PhD L5 and L6, where we have April 11 data of MET7, where we have amplitude, visibility amplitude, and over different baselines, the length between different telescopes on x-axis. And we have some internal library which can do this MCMC distribution plotting, which is corner plots. We have named it a TARDIS module. So it gives us some sort of flavor, our own flavor to this particular existing module. Although it takes a lot of time, we are still working on the efficiency of this thing. But right now we have this working prototype for this thing. And then I think this won't be necessary. This is just an example of reconstructing this particular image using another Python library that was created by EHT members, which is EHT imaging. And we use that library to basically reconstruct that images using simulations of radio telescopes all around the world, and use that to see how we can see that image if we have those telescopes at some particular location around the world. Okay. So the code is available at this website. You can go and pull some requests or pull some issue, and if you have any requests or any issues, you can feel free to contact us. We have these additions that will be adding up in coming time, which is space VLBI, and adding more ray tracing routines, which is adding up more models and doing more relativistic stuff. So I guess that was it. Thank you. Sorry, I took up a lot of time in the starting slides.
Well, it's
All right.
fun. I think that so there are 3 questions on Slido. I think it'd be great to take those onto Slack.
All right.
So please check on Slack and to follow up on this, and it'd be great.
Yeah, definitely. Thank you.
Okay. All right. So next we would ordinarily have Clark Zinzao from Anyscale. But Clark is trapped in an airport, and he's created his slides. Let's see, let me get the right one here. So it would be a shame to not show his talk, because especially I want to get the information out there about Ray, because I think that we don't know about it very much in high energy physics, but it fits very well into the kinds of things that we want to do, especially since we've been doing a lot of preliminary work using Dask, and Dask has some scheduling shortcomings that we're going to run up against as we get larger. Ray would help us to scale to much larger analysis systems. So the talks that I've put up here, these are the slides that I'll be presenting. This is Clark's talk at the Dask Summit. We had the option of just playing through his talk on YouTube, but I thought it would be better to just include a link to that in case, so that you can see more details there as he goes into the full details of this project. But I thought that it wouldn't be a good use of our time here to just be playing a pre-recorded canned talk, something that you can watch offline anyway. So without further ado, I'm going to try this admittedly terrifying prospect of giving Clark's talk, having just seen his slides this morning. So I'll be filling in with what I know about it, and mostly going at kind of a high level. I won't be going in any slides that go into a lot of detail. I won't be going into those details, but I'll just be sort of giving a high level view of this.
Jim, On behalf of organizers, I would like to say that you're probably the best candidate to do this talk. So good luck.
Thanks. I will take that good luck. Okay, so Ray for large data scale processing. So what's this talk about? It's about two things, about Ray and its ecosystem, and data processing on Ray with a focus on using Dask for data processing on Ray. This will also introduce Dask for those of you who are not familiar with it. Some of you will be familiar with it. Some of you may even be using it, particularly in coffee analysis. So a bit about Clark, not me. Clark is a software engineer at Anyscale. Anyscale is the company that is behind Ray in the same sense that the company called Databricks is behind Spark, or Anaconda is behind Numba. It's one of these things where it's an open source product, but there's a company that productizes it for particular commercial clients, and therefore they put a lot of development into it. So Clark is working on the core Ray system, focusing on supporting large-scale data processing. And before Anyscale, he was a Ray user. Ray it's a new product, but it's been out for a few years. So what is Ray, and why should you care? So Ray is a distributed task engine, providing simple API for building distributed applications. Actually, let me go higher level than this slide. So in the long view, actually, earlier, Ben gave a talk showing the transition, the development from Hadoop to Spark to Rapids, where at each stage, loading and unloading of data was simplified. Hadoop was sort of the beginning of this big data movement around 2006. Providing sort of a base layer, an infrastructure into which MapReduce jobs could be run. And then Spark was an improvement of that expanded upon from just map and reduce to arbitrary functionals. And it came out of the Berkeley AMP lab. Started as an academic project, Spark did, and then it became an open source thing with a lot of commercial input. Ray is the same way as that. Ray also came from the Berkeley AMP lab, or I think maybe the AMP lab has changed its name. It started as an academic project to improve upon Spark, and now it is getting into widespread use in industry. And it's improving upon Spark in two ways. One is that whereas Spark was purely functional, the workers didn't know any state. Ray is stateful. The workers in Ray can remember what has happened before, and we'll be getting into that in the next few slides. And the other is that whereas Spark was entirely built in JVMs and it has a PySpark interface, we in HEP have had a lot of trouble using all of our Python heavy and C++ heavy tools in Spark because of this bridge. And we've done it, and there are projects that have successfully done it. But this bridge between the Java virtual machine and the real machine has been a problem for us. Ray was developed in Python, so it's already native computing. Python-centric, although there are Java and C++ APIs. Okay. Right, so the Ray API and programming model. So this on the left is kind of what Spark was all about. These pure functions and distributing them. This is something that goes beyond what Spark can do. A class like this counter that has internal state. And so it remembers the previous value. And so when you call a method like increment, it's able to, atomically increment this number and not get that wrong. In Ray, these functions are called tasks. It's the same word as is used in Spark. And you make tasks by putting a decorator, this Python decorator in front of it. Actually, that looks just like Dask. But now there's also this this actor, which is what classes with state become. And all of them are made remote by putting @Ray remote in front of it. So Ray is a collection of actors who remember their pasts. The actor model is a model of parallel computing that goes way back to the 70s. So in fact, it is widely used. There's a library in the Java and business world called Akka, AKKA. This Akka library implements actors, but this is bringing it to the Python ecosystem. And I guess you can also specify a number of GPUs. That's nice. Of course, I don't know the details of how you use that. So the principles of this, the bottom substrate can be a number of systems that are already out there. There are, so AWS, Google Cloud Engine, Azure. These are all clouds. Kubernetes, you can run this thing on Kubernetes, and you can run it on a laptop. So you can do your small scale testing on a laptop and then scale it out. That's just like Spark. That was a good idea. So then they break the architecture of this into an autoscaler with the high level task actors that you create in your program on top of that. And actually, when I say you create in your program, this might actually be like the coffee developers or other framework developers making frameworks for HEP. I'm not sure whether individual physicists are going to be writing to this API or not. Okay, Ray architecture. And here's where I'm not going to go into details because I really wouldn't be able to do this justice. One thing I can say about the Ray architecture is that unlike the Dask Dask scheduler, there is no single point of failure. This is something that people who are developing distributed systems think about a lot. Single point of failure. If this one node dies, does the whole cluster die? That's a single point of failure. With the Dask scheduler, there is one scheduler task, and if that task dies, the whole job is gone. Ray was developed with the idea in mind that we're going to have, well, first of all, multi-user systems, and therefore they have to be robust. You can't have one user, taking down the system. Whereas Dask's point of view is that one user creates a system, uses it, and takes it down. So Ray is really built from the ground up to be one of these large multi-user systems. Okay, details of what the clusters look like. Raylets, I suppose, are pieces of this. I'll just zip on past the details. So comparisons to other systems. So we have stateful computation, that's new. Actor fault tolerance. The performance, millions of tasks per second, millisecond latency. So these are the actors have to be very lightweight. Shared memory, zero copy serialization. This is done with Apache Arrow, which you've probably been hearing quite a lot about recently, because it allows for nested data structures to be zero copy serialized and shared among processes and across networks. And Arrow data structures have a one-to-one relationship with awkward arrays. So conversions between them can usually be zero copy. So that's another reason, what the data that we're sending around between these things is arrow. So it's efficient to move data across. And that's part of the problem that we were having with Spark and PySpark. Yeah, multi-language, C++, Python, and Java. And Java's still in there because business intelligence really needs that in industry. Why is Ray great for data processing? I think I could talk about this. The heterogeneous resources, meaning CPUs and GPUs, and different kinds of hardware, which we're going to be seeing more of in the near future. Distributed in-memory object store. This is the Apache Arrow that I was talking about. Part of the Arrow project is a memory store called Plasma that very quickly moves Arrow objects around among processes. And FastSmart decentralized scheduling. This decentralized scheduling is the 0 point of failure that I was talking about. Okay, so given that, you might need to say that this task requires so and so many CPUs, or it requires a GPU. We can put those kind of requirements on a task, so it'll go to hardware that actually has that, or it needs to have enough memory or whatever. And this is talking about the object store. This is the Plasma object store, which is what allows for 0 copy reads on the same node of workers using shared memory. And the reliability is that if not everything fits into the memory of this object store, it spills to disk. These are details that I will not be able to speak to. Ray ecosystem is focused a lot on ML and distributing ML, machine learning, I mean, which will be of interest to a lot of people here. All right, now Dask on Ray. What is Dask? Dask is a parallel computing library for Python geared towards scalable analytics. And they provide parallel NumPy array and data frame abstractions, and in the nearish future, awkward array abstractions. That's something that we're going to be working on. And so these provide the same interfaces as NumPy array and pandas data frame and eventually awkward arrays, but do the computations in a distributed way. As a user, you see this only in one place, where at the beginning you say, these are distributed objects. Your whole computation on it is just is a description of a computation. And then when you say .compute, then it actually runs it all. And when it runs it all, it can run it all in a distributed way. Is this an example of that? This is kind of an example of that. We import Dask array as DA, and then use this Dask array as though it were a NumPy array. Or we use this Dask data frame as DD, and we use this data frame as though it were a data frame. I guess this is a scikit-learn integration, which is great. I was just answering a question about this yesterday, that scikit-learn has to be in on it, has to be aware of these, the fact that your data is distributed in order to implement a distributed algorithm on them. So, so with these interfaces, they all know about the fact that this data is distributed. All of these steps in the process, like x plus x transpose minus x mean, all of those are just accumulating a set of instructions of what you're going to compute. And then at some point you say .compute, and it actually runs it. And where it actually runs it whether on your local machine or distributed across your local machine or distributed across a cluster, is something that you can configure separately from actually doing the calculation. So you get to separate your analysis code from how you run your analysis code. And that's great because you can test it on your laptop and then run it on a cluster. And so Dask's three main components is it has these collection types, Dask array, Dask data frame, Dask bag. Dask delayed, this is just labeling a function as delayed. This is actually just like Ray's remote function, remote task. And then in the future, there'll be another box here called Dask awkward array. So there's these collection types. You do stuff on the collection types and it creates a task graph, a set of instructions of what you want to compute and the dependencies among all of those steps. And then it goes to schedulers, which could be single machine or distributed. And that's what actually runs it. Do you run it all on your local machine or do you run it distributed? And the thing is that Dask has already implemented all of this great stuff. And its scheduler, as we'll talk about on a slide that's coming up, is a bit lackluster, designed with single user scientists in mind. And we can just, because of the modularity of all this, we can just replace this one piece with Ray. So that's what this Dask on Ray is. So some more detail about what a Dask graph specification looks like. This is using Dask delayed, where you can delay these functions. You can delay like the increment and the add function using a decorator. And then when you call them and you say that this, if you say at Dask delayed of this def inc, then when you call inc on X, it's not going to run it. It's just going to add it to the task graph. And this is what that graph looks like. The Z, which is the result of this that you want to see, consists of adding Y to 10, and Y consists of incrementing X, which is 1. And then when you say Z.compute, you get the actual value of Z computed on some system. Task scheduling and execution. This is this is the thing that we're wanting to fix here. So what are we saying about this here? Dask provides several scheduler options, a local synchronous scheduler. So that's like running things on your laptop. A local multi-threaded scheduler using a thread pool, or multi-processing scheduler using a pool of processes. The difference between a thread pool and a pool of processes, both of these are running on your computer. It's just a question of whether you have only one Python process or multiple Python processes. And generally, you'd want the multiple Python processes because Python has a GIL, a global interpreter lock, that will prevent good parallelization with threads, unless most of your computation is in compiled code. And then a distributed scheduler, and that's really what we're focusing on here. This is for the big jobs that are going to go across a cluster. The architecture is that you have a client. This is you running your thing, and then the scheduler is the thing that you remotely send the task graph and the data to, and the scheduler splits it out to workers. And as I was saying with the single point of failure, if this dies, then there's no way to get the data back from the workers to the client. So the pitfalls of Dask distributed. So this global distributor is both a bottleneck for data streaming through and a single point of failure. So there's no scheduler fault tolerance. If it's dead, the whole thing's dead. And maintenance inspecting the task graph state adds overhead. The scheduler is written in Python and inherits Python's performance characteristics, so like the GIL and also just running anything in Python. And can't be natively scared would have to resort to sharding schedulers. I don't know what that means. These
Jim,
clients are, oh, yeah.
Sorry, just so you're aware, you've had about 25 minutes.
Oh, yeah.
And there's two
Yeah,
questions
how
on the slide.
Oh, yeah, I should do that. And actually, have I said everything that I want to? I might have just done that. I might have made all the points that I can legitimately make. Actually, I really want to show this. All right, where's the question? There's the questions. So let me talk about this. So questions. How would you compare Ray to e.g. Nextflow or SnakeMink, given that you know these frameworks? Well, I don't know these frameworks, Nextflow or SnakeMink. Is there support for batch systems like, I didn't see that listed in the slide, whether there's PBS, Torque, Slurm, so actually, I don't know if traditional batch systems are going to be able to provide enough of a interface for Ray to be able to do what it needs to do. I think that the most promising option for it is the fact that it runs on Kubernetes, and a lot of our HEP ecosystems run the new ones. You know, a lot of new developments are being developed on Kubernetes. So I think that Kubernetes might be the way that we run this. But that's very much a non-expert opinion, and I don't know what Nextflow or SnakeMink are.
Stab at this.
Okay, good. Yeah. Please do.
Oh, sorry. So hi, I'm Nick. Jim pulled me in here to answer Dask-related questions. I thought I'd chime in here just to say that this is maybe one example where Dask, and this kind of addresses the next question, is one example where Dask has a bit of an advantage over Ray is it's simpler in some sense. It's like a pure Python set of server client systems. So putting it on top of batch systems is very easy. And there is Dask on Slurm, Dask on PBS, Dask on whatever, you name it. Whereas Ray has more of a, a service architecture, right? Where there's these persistent services like the object store and the various multi-scheduler systems and the message passing. And so in that sense, Ray may be a little bit more difficult to set up than Dask on a given set of resources, especially if the only way you have to access them is through a batch system. Now, that said, I wouldn't be surprised to see Ray on batch because people, I believe, have even managed to make Spark deployable on batch. And I don't think there's anything more difficult to deploy than Spark at this point. So it's probably possible if someone takes initiative, but I don't think it's their lowest hanging fruit. They're probably much more interested in making it deployable on Kubernetes, which is much more in the wheelhouse of Ray. So.
Yeah, and then even if it turns out to be possible, that might kill the performance that you wanted from it. I don't know. So actually, I really don't. Yeah, so I don't know. And it's worth checking with Dask to find out if they have these kinds of backends, and I just don't know about them. If that's totally possible. I want to answer this one because it's easy. Ray, is it free software? Yes, it is. Yes, it's free, just like Spark is free. So how about this one? Personal suggestion for HEP projects in the HEP ecosystem, what should be a preferable choice for scaling Dask or Ray? Well, the thing that I was very excited about this project, and the reason I wanted Clark to speak about it is because we can take the best parts of both. Also, I think that these questions of whether the system is being distributed by Dask or by Ray or by, I can't think on my feet, is something that is usually one step away from the physicist. people are designing these query services to set up a system so that at Nebraska, for instance, there's the Coffee Casa project, which I believe is using Dask, and so as a user, as a HEP user, you would submit your work there. And tools such as Coffee insulate you from the choice of backend scheduler. But so that much said, what I think should be done here is that Dask was designed around the task graphs. This is Dask's sweet spot. This is what Dask does really well, is the task graphs and the collection API. It is a fact that the scheduler was an afterthought. It was added because they said, well, if there is no scheduler, then what are people going to use these task graphs for? And that was the spirit in which the Dask scheduler was developed. Ray is focusing just on this distributed problem. So I think they dovetail together perfectly. They should be used together in exactly the way that Clark was describing. There's a question here. What about data provenance? Workflow managers offer tracking of how data is mangled. Do you mean managed, maybe? Activity, user, entity tracking. Does Ray offer such functionalities? That is the sort of thing that would be built as a higher level thing on top of Ray or any such scheduler. And the fact that Ray has state, I think is going to make that easier. It's going to make that more performant. This kind of tracking, and particularly, even if you're thinking, oh, all of my functions are pure functions. I take data in, and the results out are a pure function of the data in. There's still a lot of complicated things that need to go on, like caching, in order to do that well, and then wanting to send jobs to where the data is already cached. Those are all very stateful things, even if your physics process is not itself stateful. And I think that some of this data provenance is also stateful and can benefit from this model. So I think we can clear the questions, and they'll go on to Slack as usual. I'm also chair, so I have to ask myself, am I running out of time? Oh, no, I did. This is the end of the talk. Thank you, everyone. We have a break. We should reconvene at 40 minutes past the hour, which is 20 minutes from now, a 20-minute break. Do the other organizers concur that 20-minute break start on schedule?
I think we have to start on schedule. I think some of the next talks have to happen at the time they were scheduled. Some people have to leave. So I think, yeah, we'll stick with that.
Okay, so we're sticking to the schedule.
We should say thank you to you, definitely, for jumping in and doing such an amazing job. So yeah, thank you, Jim.
Okay, thanks. I'll see you in the next session. Have a good break.
Hi, John. Hi, everyone. So yeah, welcome back. And we are, can everyone hear me okay?
Yep, I hear you.
Excellent. So yeah, we are going to get started with the last session of the day. We've got 4 talks, I think, for a range of different experiment-specific uses of Python. Joran Angavara is going to start us off. So am I saying it right, Joran? Joran? We can't, can you, we need you to unmute. Hang on, I understand what happened. We need to make you a host. That would be the ideal, but you should be able to unmute yourself now, at least. Did you get, I asked you, I invited you to unmute. Did you manage to see that? Jim, can you make me a host?
Oh, I'm sorry.
Wonderful. Thanks so much. Yeah.
Perfect.
I was trying to unmute, but it didn't work.
Okay. So
Yeah,
I'm not sure saying it right. You're on, but you should be able to share your screen, and you can take us away. I'll let you know when you've had 20 minutes, and then you've got another 10 minutes for potential questions and discussion.
Yeah. Thanks a lot. Can everybody see my screen and hear me well?
Perfect. Yes.
All right. Thanks so much. My name is Johan Angevaren on behalf of the Xenon Anton experiment here on PyHEP. Whereas we're actually not doing so much high energy physics, but actually low energy physics because we're doing a rare event search. But nonetheless, let me explain a little bit how we use Python in our experiment. So our experiment consists of many institutes all around the world, and our aim is to detect dark matter. To that end, we have here our time projection chamber filled with liquid xenon, where with one day we hope to find a dark matter interaction. It's located in Italy, which you see here on the right side of the figure. Now, let me explain a little bit how this experiment works. So within this vessel, we have liquid xenon, and if a particle interacts, we create a first scintillation signal, which we call the S1, and the electrons that are freed in that interaction are drifted upwards because of an electric field creating an S2. And with those S1 and S2, we have all the information we need to do the physics, which may one day allow us to find dark matter. Now, of course, we need to reconstruct this properly, and to that end, we have 500 light sensors, PMTs, both at the top and the bottom of this detector. And each of these PMTs is continuously being read out. So they measure pulses over time, and we do this. This is the only place that where in the software stack C++ comes into play. We do this with readx at a rate of about 50 megabytes per second. So let me stress again that each of these channels is read out in a self-triggered way. That means that there is actually no trigger globally applied to this data. Nevertheless, we're able to store all of this data because we're a rare event search. So all of this data is making it to disk. And from then on, it's Python only. So in order to reconstruct what went on in the TPC, in our detector, we need to first group all these pulses together to make the S1 and the S2 peaks. If we then have those peaks, we again have to group them together to get the real event, what happened in the TPC. And with that, we can do the physics we want. Now, let me showcase how our software works. And rather than talking about it a lot, I'd rather start off with a demo. I must apologize in advance that I didn't upload the notebook because of the amount of data that's created. It would just take a long time. But all right, so in the following demo, we're gonna look at how our software would enable us to look at the detector live while we're, for instance, calibrating it with a radioactive source, a krypton source, And we're just going to look how we can use this software to look at the data. And next, I will also focus on, if we have the data, how we can do multiple analysis at the same time. But let me just start off with a demo. So imagine I'm now on my own computer starting up a fake DAQ, which is processing the data live. While we're doing that, we can already look at the data and see what's going on. If we look inside this graph, we see for some energy ranges how the event rate is building up. The different lines indicate different energy ranges. We can also see the different types of peaks. So we have these S1s, which are very sharp, and S2s, which are very broad. And this is all happening live on my own machine. You, by the way, can also look at how much each of the channels is seeing. And this can go on while we're doing a krypton calibration to actually see live the development of a radioactive source building up. Now imagine that you're an analyzer, you now want to look at this data. Krypton has 3 characteristic peaks, which you see over here. There's 3 of these peaks characteristic for krypton. However, an analyzer notices that there's also a lot of stuff at the low energy and comes up with a brilliant idea to get rid of this low energy stuff by changing a configuration for the number of PMTs needed in order to define a peak. This analyzer changes the configuration that is involved, which is this 50, it changes it to saying that each peak should be seen by at least 50 PMTs. And while it's doing that, it's asking the software, okay, well, then just give me the new data as if we were processed with this setting. And within just 18 seconds, we have reprocessed this data. And of course, we are targeting this low energy part of the data. And now I would like to show you that there is also something interesting going on if we look at the amount of data we have processed. Don't want to go into details of what all this data is, but if you now look in our process data folder, you see actually that there's 2 copies of peak basics, whereas just only 1 copy of records and pulse counts. I will come to that in just a moment in the rest of the presentation. But in order to, we actually also do this online processing live on the entire Xenon Anton data. So that means that we're at the DAQ level already doing a full reconstruction of our entire data chain. So going from the raw signals all the way to these events. And this comprises doing the baselining, finding the hits, doing the peak finding, and actually this peak finding you might call a trigger, as before that we don't actually have a trigger other than the self-trigger of the digitizers. Also, when you do position reconstruct using neural nets using TensorFlow, we apply corrections. Everything is happening faster than as fast as the data is actually coming in. And to be able to look at this data, we also ship a part of it into a Mongo database, which allows people to actually look at this data online as data is being collected. So within 30 seconds, you can anywhere in the world see the fully reconstructed data as it was detected in the DAQ. And we actually made it even easier for people that you don't even have to open a terminal. You can just ask via Slack for the latest status report. So how do we do all this? Because I said this is all done in Python. How we were able to get this all doing all this reconstruction as fast as the data comes in? Well, of course, what you need to have is performance. And when we were upgrading from Xenon 1 ton to Xenon N ton, we also upgraded our software. So in the old days, we were able to do just 200 kilobytes a second per core. Now with the new software, which we call Strax, we're able to go much faster. So let's look a little bit deeper into how do we actually get there? How does this work? The answer is this Strax, the streaming analysis for Xenon. And our software is divided in this generic Strax framework and the Xenon Anton specific Straxon framework. So in Strax, we have all the generalized and optimized code. As I will explain a little bit later, we're relying heavily on NumPy and Numba to make all this stuff fast in Python. The detector-specific software, like choices, how many PMTs you need in order to define a peak, is all stored in Strax. Both are, of course, relying heavily on continuous integration, and the core code is public, whereas analyses and detector-specific conditions are, of course, private. All right, so let's look a little bit deeper into what is our goal for this software. So the goal is to get from these raw PMT traces to the events. And in the meantime, we also, of course, need to cluster those PMT traces correctly in order to build the peaks. And we have chosen to go for a tiered data structure and a modular processing framework. So how does it look like? Well, at the lowest level, of course, we need to read out what the DAQ spits out. So as I said, we have a reader software in C++, which just dumps the data as it comes out of the digitizers to disk. Then when we start reading this in with Python, we have a DAQ reader, which is able to read the format and convert that to this to the Python format we are using later on. We then have to process the pulses to get the peaks and events. And as you can see, and as you can imagine, that at the lowest level, all these raw PMT traces, there's a lot of data there. So this is typical for a 1 hour run. However, if you go further up in the chain, you're doing the triggering, you're doing the triage, you're making selections, the data becomes much smaller very quickly. And in the end, when we're talking about events, we're orders of magnitude smaller in size. And by the way, illustrating here all the processing steps along the chain, which we call plugins, as Lego blocks, because we went for a very modular approach, which makes it very easy to interchange one of these plugins. For instance, in the demo I just showed, there wasn't actually a DAQ reader, but instead there was a simulator plugin which simulated the data. Now we wanted to know how we make this fast. So for that, we need to look a little bit further into how is the data shared in between those plugins. And the answer is that, for instance, when we're looking at pulse processing, we look at a given chunk of data. We organize all of our data in time intervals, which we call chunks. So there's a chunk of data which is being processed by the pulse processing, and after it's done with that, it will send it out to the next plugin to be processed there. We can do multiple chunks at the same time, here illustrated with the conveyor belts, because we are able to multi-process all this. Now, each of these chunks is organized in a tabular format. That means that the arrays are of fixed length. We use NumPy structured arrays for this, and everything is a fixed length. However, this may not sound like a very intuitive choice, for these S1s are very short signals. So if you're talking about a fixed buffer length, such an S1 signal easily fits into this S1 in this buffer. However, S2 signals can be very wide, up to microsecond long. And that means that we sometimes need to split all these raw traces into multiple buffers, thereby introducing some extra bookkeeping. However, of course, with this extra bookkeeping, we're later able to reconstruct one S1 followed by an S2. But it may not sound like a logical choice, given that you know that we have such different data for S1s and S2s. However, it is what makes our software fast. Because of this, and because of the great features from NumPy structured arrays and Numba, we're able to do all this processing live in Python. So using just-in-time compilation, most of especially the low-level software is all very much relying heavily on Numba. And because of this tabular format, we're able to do this auto-vectorization, which makes it really fast to go through all of this data. Now, there was also a second question, which I already briefly touched upon in the demo, because now that we have a very nice fast framework, we of course want to use it for the many different types of analyses we can be doing in Xenon and Ton. Therefore, I'm going to zoom in a little bit more onto these plugins, and I've of course been very much making this a lot simpler than it actually is, because actually each of these Lego blocks shown here can consist of multiple sub algorithms needed for the processing. And each of these plugins has a fixed set of attributes. So it has some options, it has a version, it knows what kind of Lego block it was built upon, and it also knows what kind of data it provides. Then, of course, it uses the highly optimized code we have in Strax in order to do all this fast. Because if we're thinking about the experiment, we might want to change one of these options, as I showed in the demo. And if this is happening, we, of course, still want to know what data is belonging to what plugin, what options were used. So for that, we use these incomprehensible hashes, which you might have already seen in the demo. So all of our data has a given run number, the kind of data it is, and also this hash, which is behind it. And that hash is an encoding using hashlib of the entire ancestry on where the data was built on. For instance, if we look at Peaklets, it's produced by a plugin, which we call Peaklets, which has a given version. It has some options, and it's built on top of the records, which has a similar format again. Now, this entire dictionary of how things were built up is encoded in this hash. And now if we want to change something, for instance, we want to use a different gain model, and you ask for this, the data which belongs to this, the ancestry changes, and therefore we use a different hash for encoding this data. However, of course, the data which is below that, the records, where we actually do the pulse processing, doesn't change when we change something which is associated to Peaklets. Therefore, in the example I also showed, the records were actually only produced once, because we were only asking for one configuration. The higher level data, where we changed the configuration, was produced twice. And this is how we allow for partial reprocessing. And of course, if you think about the stack of how we build up our data, you mostly want to do this for high level stuff, where actually most analyzers are working on anyway. If you change something very low in this processing chain, of course, you then need to reprocess a whole lot of data. Now, this may sound complicated, but we try to make this easy for the average user of our framework, because there's always so many different needs, but there's only a limited number of developers. So to make things simple and robust, we set up everything like these options and these plugins for a given search. For instance, if you're talking about Xenon 1-ton data, you might want to have a specific set of options. When you're working on detector simulation, you might maybe having some different options. But everybody who's looking for Xenon N-ton data, position reconstruction, or dark matter, or anything else concerning Xenon N-ton, these people all want to use the same options. And we bundle those options in the context. The context is a centralized object within our framework. So also when you're changing only one of these parameters, you're still able to use the N-ton context because maybe you've only changed something very high up in the event level. This context is talking to all the parts we have been discussing so far. So when a user asks the context for some given data, the context will first compute, all right, so with this data you're asking for, how does it work together with all these plugins and options? Do I actually have the data stored already? If so, it will return it, but if not, it will just go all the way down in the data chain to find where it first finds some data, like the lowest level data, that is consistent with what the user asked for. And then it will start processing it and return it to the user, as well as store it to disk, so that when next time or someone wants to use it or the user wants to use it, it's still there. All right, so Xenon Anton, we have gone for a data which we organize in chunks, so fixed time intervals, and in a tabular way we organize our data in order to make processing fast. We're using modular design of our algorithms and a tiered data storage approach, where the high-level data is much smaller than the low-level data. Because we keep track of the entire ancestry of data, the entire lineage, partial reprocessing becomes very easy. And given the speed of our framework, people actually do this quite a lot. So with this, we get from PMT signals to events in as fast as we can actually take the data. And all what I've been telling about is not only limited to time projection chambers, so where we are looking for dark matter. For instance, our veto systems are using the exact same framework to talk to the PMTs used for instance, the neutron veto and the muon veto we use for tagging backgrounds from neutrons and muons. So with that, I would like to conclude. Thanks so much for your attention.
Thank you very much, Joran. And you actually have a handful of questions on Slido. I've dropped a link on the chat. I don't know if you want to share that to go through the questions.
So the first question, you can see my screen, right?
Yeah, that's great.
So what I was just showing wasn't real data, but actually it was based on simulated data, but the overall real data looks really similar, and also the workings are exactly the same. Right there. The next one. Is any of the general software used outside the Xenon Anton community? Good question. So the general software at some point was also, there were some searches by Nexo to see if they could use it for their MC chain. I must admit that I'm not fully up to date whether they're actually using it. But also small scale experiments, like for instance, we have here at our institute at the lab, use the same general software, but it only has 2 PMTs. So those kind of very specific things are changed, but the general software is also used for these small experiments. There are various dark matter experiments out there. Are these collaborations doing as we are in high energy physics and trying to share as much a dark matter ecosystem as possible? If not, why? Well, that's a very good question. So our main colleagues are from the US and from China, and we don't use the same kind of analysis software. We are at this moment at an entire different paradigm, whereas we are only using Python for all the processing. Our US colleagues have gone for C++ all the way, and it's just a very few last bits where they are using Python. So already there, it's completely different. And it's also dictated a little bit by the design choices made in the DAQ. Whereas we have gone for the design choice to do everything in software, our colleagues from the US are doing a lot of FPGA triage already very low level at the DAQ. Maybe for the next generation experiments, we are trying to get together much more closely, but at this point, we're quite diverse in these ecosystems. I hope that this has answered your question. So it wasn't real data, it was simulated data. Do you share the cache lower level output between collaborators or between institutes? How is this managed? Yeah, good question. Maybe I have a slide on this. Let me see. Okay, no, unfortunately I don't. So it's a good question though. So all of our data is shared between our own collaboration. So this raw data we are getting from the digitizers themselves is so massive that it is very hard to store in one place. So for that, we send it out to the data storage facilities. It's very easy to download it, but only on request. Somewhere intermediate, so maybe I can share my slides again. At the intermediate level, when we're talking about peaks, this data is shared between everyone and can be opened. And so when we do a reprocessing, we are also mostly focusing on this aspect because this step is so fast and so easy that analyzers can do it just on themselves. And we're having one centralized analysis software facility where all of this is stored and everybody can do their analyses. Now I need to get back to the question. Do you exclusively use Python for the high-level analysis, or is it the usual mix-up of C++ framework for inside the experiment? So we only use Python. Everybody uses Python for the high energy, for the high-level analyses. So there's no mix-up between C++ and C. There's no real war going on there. It's only for our simulation software that, for instance, GN4 and stuff is coming into play. But for the high-level analysis, it's only Python. How is the performance of the US C++ framework compared to? I must admit that I'm not familiar with the. Okay. So you're talking about our main colleagues. Yeah, very good question. I have actually never tried using their software, also because their software isn't publicly available. Otherwise, I would be very interested in trying this out. I wouldn't be surprised if our framework is doing quite well compared to them, but yeah, I must admit I have never used their framework, and I also cannot because it's not open source. Are there any open science initiatives in Xenon and Ton? So you would mean the sharing of data in Xenon and Ton? Unfortunately, as far as I know, there aren't any initiatives to make the data itself publicly available. All of our software is, and we highly also encourage people to be able to run these tools. For instance, you can very easily run our simulation software yourself. But as far as I know, there aren't any initiatives to share like the low level data. It's also quite hard because it's so much data. There's questions keep on coming, which is good. Yes, sharing data and tools. Yes, I agree on that. How do people that have to deal with GN4 and C++ find it if they're now more used to getting work in Python for the rest of the experiment software? Yeah, it's a good question. There are many people actually are completely fine with having this mix-up, but there's also a bit of a shared of distributed tasks, right? So the people who do most of the heavy GN4 simulations usually aren't the same people doing the very high-end analysis. Sometimes they are, but most of the times they're different people. And we just work together in order to bring everything together. So so far there's no real struggle there. It's also because we have been using Python so much that it's kind of a given. It's mostly for new people entering our collaboration, which sometimes have to get accustomed to using Python in this way.
Well, thank you very much. That's perfectly timed as well, because you've finished bang on the mark. So yeah, thank you very much, Joran.
Right. Thanks so much. Let me
We'll
stop
copy
sharing.
these. Yeah, we'll copy these questions onto Slack, and I know you've answered them all, but if there's anything you want to add or there may be follow-ups, so it'd be great to get you there. So yeah, and our next speaker, Laura.
Hi, can you hear me?
Yeah, we can hear you.
Okay.
You able to share your slide?
Can you see the screen?
Perfect. Yeah, and well, I'm excited to hear about this. It's a fantastic name. Yeah, so I'll let you know when you have had 20 minutes, and then you've got 10 more minutes potentially for questions. And if you keep an eye on Slido, that's great. But otherwise, I'll let you know if questions pile up and so on.
Okay. So hi everyone. Thanks for letting me talk about my code, Lardon, which is a tool in Python to reconstruct liquid argon data. So, well, first of all, what is liquid argon TPC? It's the technology that is foreseen to study neutrino oscillation in the future Dune experiment. And how it works, so a liquid argon TPC is a chamber filled with liquid argon in which we apply a uniform field, a drift field. And when a charged particle crosses the detector, it will locally ionize the argon and along its path. And thanks to this drift field, the electrons will be attracted to the anode. And if the field is uniform, then the electrons will drift at a constant speed that we are supposed to know.
No,
and then,
can you just make it slightly bigger? If you can just increase the size. Yeah, that's much better. I don't know if you've lost the edge. Yeah, that's perfect.
Yeah, and then these electrons, so they are attracted to the anode, and then they are collected either with strips or wires along 2 or 3 projections in space and time. And in Dune, the scale of this detector will be modules of about 60 meter long, 50 meter high, and 40 meter wide. So it's very big, and in order to be sure that the technology works, we built prototypes at CERN, and we tested different technology. One of them, the one I'm working on, is called the dual phase, and it has the specificity to amplify the electrons just before they're collected in a small gaseous layer here with this device called LEM. Anyway, so this prototype, called the ProtoDune DP, it took cosmic ray data in 2019 and 2020. Its volume was 6 meter by 6 meter by 6 meter. And you have a picture of the inside of the detector here. But due to some time constraints, we could only instrument half of it. So the surface where we could collect data is 6 meter long by 3 meter high. And it's actually made of 2 subplanes that we call CRPs here. And in the dual phase technology, we have 2 views that are orthogonal from where we collect the electrons. And these are the 2 views here, view 0 and view 1. And you have here a reminder of the convention in Lardon. And so the reconstruction, what happens, the problem is that things happen inside the detector in 3D. And what we have is only 2D projection. So the goal is to retrieve what happened in 3D from those projections. It seems not very complicated at first, but there are actually problems that make it more complex that I've shown here in this fake data, but you will see. So these are the kind of image we'll get from the data. So the color represents how many electrons we collect. Here in the y-axis is the time bin, so the time at which the electrons arrive, and in the x-axis at which position in the detector. And we have the 2 views, so the projection of here, one track that crosses the detector. So here it's completely ideal case, but in real life it's actually the electrons, it's a cloud, so there is some diffusion. So where the signal is maybe not that clear. And there's actually some random deposition. We can have more charge deposited here or there, so it's not as nice. In the detector, we can have channels that are either switched off, like here, or maybe too responsive. We can have random hits here and there due to, I don't know, radioactivity, noise, some photon converting, whatever. And we have the noise here, for example, a white noise that is added. And finally, we never have just one track, but usually many tracks superimposed. And the goal would be to find who goes with who from the two projections. Here we have two tracks that start and stop at the same time in the two views. So who goes with who? This is the game of the reconstruction. So the approach that is followed in Lardon is actually very classic. So first we have those images. We will try to remove the noise. And once we have done that, we will identify where the hits are. And we will build 2D tracks in each view as like there are lines, and then try to match the tracks from the two views to build the event in the 3D. This is a fake event, now a real one. So this is one event taken in October 2019. We have 4 images, so the 2 CRPs that I talked, and the 2 different projections, the 2 views. So the y-axis now has 10,000 beams that represent 4 milliseconds of data, and the x-axis has 960 beams, which represent each 3 meters. We can see that in this event, there is, for example, here a couple of channels that were switched off. Here, maybe 2 responsive channels here. And the color represents how many electrons we have collected, and we can see this nice muon crossing. And we can, by eye, find who goes with who in terms of projections. For example, this track here would go with this one because they start and end at the same time. And they have patterns like delta rays that we find in both projections. Just for your information, the tracks appears bended. It's not like we have magnetic field or whatever. It's just because we had a technical issue in the detector. So the first thing we do, as I said, will be to remove the noise. So there are 3 kinds of noise identified in our data. The first one is the white noise, some random ADC fluctuation. Second one is the coherent noise. So it's a noise that is seen by several consecutive channels at the same time. So for example, here we can see it clearly, like several channels have the same structure at the same time. And this is because some part of the detector acts like an antenna. And the third noise is the microphonic noise, which is a slow ADC fluctuation in time and space. And this is what we see here and here. It's like the crumpled sheet. So we see this slow moving pattern here. So I will show you how do we remove this data, but this event is too big to play with the whole thing. So we will work on the subset of the event. So this smaller part here. And in terms of practicality, so the data is stored in an NP array of dimension number of channel number time beams. And on the other hand, we have another NP array of the same dimension, which is a Boolean array. It's a mask that tells whether one point is data or noise with true or false. And as we run the filters, this mask is updated, and we consider a point being data or noise if it's above or below sometimes the pedestal RMS times a certain number that we set. So first we will remove the white noise, and for that it's very simple. We apply a low filter FFT pass. So here we can see here the raw event after it has been filtered with the FFT and the difference between the two. And we have one example of one channel. So how much ADC as a function of time. So if the low pass cut is too high, for example, we can see that nothing happens. And on the other end, if it's too small, the waveform is very clear, but the difference shows that the F50 filter affected the signal as well. So we have to set a value in between these two. And okay, and then the next noise that we want to remove is the coherent noise. So from studies, we have found that this pattern can come in group of either 32, 64, or 320 consecutive channels. And in order to remove that, we reshape, subdivide the NP array in groups of the number of channels we want to remove. And in this new dimension, we compute the average noise for each time being, and then subtract that to the whole group of channels together. So here we can play again with the data, and we can apply either a subtraction in group of 32 channels, which is what is done here, or a 64, or 320. And we can see how the event is, for example, here, almost completely cleared from this coherent noise pattern. And finally, the last one, the microphonic noise. So this noise is the pattern is a slow oscillation of the pedestal in time and space. We have tried many things to remove that, either fit with sinusoid or F50 filter that, but it was not very conclusive. And the strategy we use now is to remove this noise by taking every point and computing the medium noise around the window, with the window around it in time. And we do it for each channel and each time bit. So this is a very long way to remove this noise, but it's quite effective. So the game is to find the optimal window length. So again, if it's too long, we can see here that the small microphonic pattern remains. And if it's too small, once again, okay, everything is removed, but maybe also the signal is somehow affected. So we have a value in between for the reconstruction, and we can see here on this, on the waveform that at the end, after the microphonic in green, the waveform is almost flat and everything has been removed. So one way to see how the filtering worked is to look at how the value of the pedestal RMS after each filtering stage. And we can see that at first we had a pedestal RMS of around 1.8 ADC, and after the filtering down to 0.5, 0.6, so almost a factor of 3 decrease of the pedestal RMS. So this was for a subset of the data, but now we can look at the full event, completely cleared from the noise, and maybe there is some tracks here that we couldn't see before, but we can see now. And the game now is to find the hits. So what we have, as I said, is this array containing the data and another array telling whether or not one point is data or noise, the region of interest. So we can take a look at what this region of interest here is at this stage of the reconstruction on our analysis. So if you compare with previous plots, you can see that everything that should be considered noise is actually considered noise. But what we want to have now is hits. So actually, what we have at this point is just a collection of points, but the hit is actually has a certain shape with a length and a height and so on, and everything is important to reconstruct for the analysis afterwards. So what we will have to do is to find a long sequences of consecutive truths, and within those sequences find whether or not this is compatible with a hit, or if it's just random points that could be signaled. So there's an algorithm that we have developed that recognizes the shape of a hit, its peak, its length, and so on. It can also recognize if there is, for example, two hits very close to each other. So it's a bit long, so I didn't put it in the notebook, but I've put a simplified version of it. And okay, sorry. And we can see the result here. So for each point, we have now a box that defines where the hit starts and stops, and the dot is the hit maximum. And we can see that this simplified version is not optimal because here, for example, we should have two hits that are very close in time, and it didn't work very well. So in order to show you the rest, I import all the hits that are found by the more complex lardon, and not this the simplified version. And and we can see it here, all the hits that are found, and we can zoom into if you want. And at this stage of the analysis, of the reconstruction, sorry, I have converted channel and beam time into actual position. So that's why we now have only one box for view 0 and view 1 and no more CRPs. And now, from this collection of hits, we want to find 2D tracks. So we do that with using a Kalman-like filter, and it works like that. All the hits are set in a R3 index. And we do that so then after we can choose a hit and find out who are its nearest neighbors. And in order to find a track, we have several steps. First, we take one hit still available in the index, find its neighbors. To initialize the Kalman, we fit a line with its surrounding neighbors, and then we propagate that with the Kalman filter. So at the last point that belongs to the line, we search for its nearest neighbor that are not yet attached to the track, and we try to test whether or not this point could belong to the track with the parameters. And we compute a chi-square for each point, and if it's below a certain cut, then it's accepted, and this is how the track propagates. Once there is no more hit close by, then the 2D track has been found, and then we can go on until there is no more hits available in the index. Once we have found a track, like this one, we run a MST graph on it with all the hits to try to identify delta rays, and they are spotted by the fact that a delta ray is potentially attached to a graph vertices, so a point that is linked to here. Not just 2 hits, but 3 hits. And here we have found 2 potential delta rays in this example. Okay, so the result on the events that have been shown you from the beginning. So the dots here are all the hits that are found, and the lines is all the 2D tracks that have been found by the code. We can see that it works quite well. It's not perfect. For example, here there is a problem. For some reason, the filter chose there's 2 tracks that cross, and the filter chose the wrong part of the 2D tracks. So it's not completely perfect, but in other cases of tracks that crossed, the filter did not make mistakes. So it's good, but perfectible. And from this collection of 2D tracks in each views, then now we want to build 3D. So what we do is we take one track in one view and try to find who could be its best match in the other view. So a best match is based on track timings. It should start and or ends at very compatible times, and the charge that has been collected in the 2 views must be balanced, must be almost equal. So every track gets a best match on the other view and vice versa. And if two tracks have the same best match, then we can build a 3D track out of it. I hope it's clear. And here is the result from the event that we have looked so far. And the thick lines are all the 3D tracks that was found with one color in one view is the same. They go together. So this one goes with this one. And here you can see in 3D how well, you can play with it and look at the 3D version of the event we have been looking so far.
Lara, just to let you know, you've got about 10 minutes left and there's a handful of questions for you. So feel free to bounce between that or finish up how you want.
Just to, in terms of, I will quickly finish. In terms of running time, it takes about 20 seconds to reconstruct an event, where the microphonic filter is the longest, and the second one is to build the R3 index for the hits. And just before, because I like this one, if we look at many events together and superimpose them and look at all the 3D tracks, we can see, and here we look at the detector from above, we see the details of the detector and this 72 amplification device that we have set. And in particular, we can see the screws and the high voltage connector and the protective layer. You can compare that with the picture on the inside. And we don't just do, this is a theta phase space of muon-like tracks that we have reconstructed. And finally, it's not just to do 3D, but also calorimetry that you didn't explain. And here we can look at how much charge we collect as a function of how long the electrons have traveled in liquid argon. And we can see a decrease due to the impurities in liquid argon. And it's a result that we were expecting. So in conclusion, it works well. And okay, I will look at the questions.
Thank you very much, Laura. Yeah, if you want to walk through the question.
So, do you use this sort of interactive plotting and widget and presentation of the results within your collaboration? No, actually, I think I was one of the first to do a notebook rehearsal talk in June, and it confused many people, myself included. But it was cool. I see a lot of bits of code. Are you somehow wrapping it all into domain-specific library to make it easy for colleagues to use and leverage? I'm not sure I understand the question. Here I put a lot of code to have the beautiful plots and everything, but I don't know. I'm not sure I understand the question.
We can take it offline.
Okay. Do the optimal denoising peak finding parameter change from run to run? If yes, do you have to find them by hand each time, or is it automated? So far, no. We try to not change them too much, but it might be needed actually. And in such case, by now it would be by hand. But it's true that an automated version would be optimal, but yeah, not yet is my answer. How do you calibrate your detector geometry, or is the installation misalignment irrelevant here? I guess you mean the two projected view. Well, by construction, they're orthogonal, so the geometry doesn't change. And in any case, yeah, if there is some tiny displacement, for example, in the two subplanes I've shown, I don't think it would be that much relevant with the data we have collected. Have you done this analysis for ND with GN4 or only with Protogen? So far it's only with Protogen, and so far Protogen dual phase, but we, for some reason, the dual phase this technology has been changed to something different, so we have to adapt it. I'm not sure for the near detector, but maybe for a single phase or for the one who knows the vertical drift. It seems that machine learning would be very well suited for this task. And do you have any experience with that? Yes, of course, but there are some people working on that. And not so much for the dual phase, because you have different gains, and maybe training the machine learning could be complicated. But as I said in the conclusion, for example, at some point we wanted to try to identify the hits with machine learning or pattern recognition, for example. So this could work. So does it work for single phase? Not yet. And if such case, what would be the change? So for single phase or vertical drift, there is 3 views. So you need to adapt the 3D matching code to have a third projection. And the shape of the of the hits are different because there is an induction layer. So it needs to be adapted to work for single phase, vertical drift, or other geometry, but it's not impossible. It's just some work to do. And is Lardon packaged? No, but available online, yes, on GitHub.
Not sure. Yeah, there was is this last question clear? I mean, I guess you talked about it.
Yeah, I think it was related to would it work in single phase or
okay.
this kind of things. I think.
Okay. I apologize slightly because I maybe rushed you a little bit on the last couple of slides, including if there's anything you want to add that you had to skip or go quickly over, certainly feel free to.
But yeah, no, the conclusion. So okay, it was in my conclusion. It can be adapted to other design and will be, and there are some parts of the code that we also maybe need to further optimize, like the running time or the accuracy of the reconstruction. I've shown you one example where the 2D track filtering failed. And yeah, and if you think 20 seconds is long for data like that, the official code is much, much slower. And yeah, and yeah, one point is it's a great tool to quickly test different kind of algorithms, much faster than the official code. But that's it. Yeah.
Well, thank you very much, Nara. And I noticed you've got 2 comments coming through on Slido, so we'll copy these over to all of the questions you've had. We'll copy them onto Slack, and it'd be fantastic if you'd be happy to copy or extend the answers there for everyone else, so it's also there as a record. But yeah, thank you very much for the very nice overview.
You're welcome.
Okay, so next up we have Johannes, and Johannes, I need to make sure you can unmute.
Can you hear me? Can you hear me well?
Yeah.
Okay, then let me try to share my screen. Can you see my slides?
Yeah, perfectly.
Okay, then I think I'm ready to go. I'm Johannes Schumann. I'm a PhD student at Erlangen, and I'm working on KM3net. So that's the reason why I'm presenting you the Python software environment in KM3net. And so first, I will give you an overview about KM3net. So it's a water Cherenkov detector infrastructure in the Mediterranean Sea. At the moment, we are focusing on 2 sites, which is Orca. It's the more dense instrumented detector for tackling the lower energy and determining the neutrino mass hierarchy. And we have ARCA, the name-giving site. It's more sparsely instrumented, but it has an in its final configuration, it has an instrumented volume about 1 cubic kilometer. And this is for discovering high energetic astrophysical sources. And so we're building those at the bottom of the sea, so it's a challenging task to build up, operate, and scientifically exploit the detector. And I think with respect to the data handling and the computation, is the challenge is to minimize the obstacles to access data from multiple languages and platforms, and in order to maximize the information from the data we take. To the detector setup, I've given you here, so basically how this works out. So we have our sources. As I said, for the lower energy branch, we're using atmospheric neutrinos. And for the higher energies, it's we are looking for active galactic nuclei, or also supernova. Then when the neutrinos propagate through Earth, we are looking for the Cherenkov light of the secondaries for neutrino interaction. And you see here an artist impression of the Orca detector in its final configuration. So the Orca detector will look mostly the same. So they're sharing the same technology with optical modules, but here the measures are for Orca. So for the computational setup, we have here on the top left, you see here the detector. It's connected via an undersea cable to a shore station. And then our main software for running the whole detector is written in C++. So we have there a tier-based processing chain and do the data write out to the computing center. And what I've given you here is the Python environment there. So we can access the data, the written out data from our file format, which is in root, and for example from the database with those tools. And we have also a large tool set for this, specifically for KM3net in Python. So for the C++ side, as this is used for the triggering, calibration, or reconstruction, this was the first thing we had for Python. So the classics, the usage in Python via pyroot and CPy. And there we had at a very early stage the focus on using it from Python and developed it that way. And when we have a look at a small coding example here, then we can do here the import with what is called AA, that's the framework name. I've taken one file from a package which is called KM3net test data, where we have all our examples for all our data formats available in order to use it for unit testing, or in this case, to give an example how the reading is done. Then you can just open an event file and dump out the data. So as I said, it's was already a focus there on the easy usage. But in all, the problem there is a little bit that you need to have still root installed. And as we have such a nice thing like uproot, we came to the package called KM3IO. So we use, we have now the possibility to access our root-based data via uproot and awkward. And here we have mainly two file formats, which are called internally online and offline. So one file format is for the detector DAQ write out, and we have the offline file format, which is for the Monte Carlo simulation data and the final event reconstructions. So as I already said, the reading of the data was previously possible, but you need to have root installed. And from our benchmarking we did on this, the pyroot was slower and required more memory than doing it with uproot. And we also have internally an optimized iterator behavior to allow this lazy readings of multiple branches. And the last point, that's more, I think this uneven data structure of because we have per event a different number of photosensor readings, what we call hits. That's in the HEP community, nothing too new. In the astronomy groups, that's not that common because there also a lot of applications have images with a fixed resolution where you can just then use multi-dimensional arrays. So this fits for us also perfect with the awkward package. And to also go into code there, let's have a look at the uproot perspective. When I open a file with uproot and do just a show on the root path in the file, then you see that there are a lot of custom structures in this file, which uproot can handle really good from the start on. So if we then go to the hit information, for example, then I can browse via the path to this branch, and I have here all the keys given in there. And as we use general purpose classes, for example, for the DAG readout and the simulation, there are also fields which are given there, which are just empty for this example file because I've taken it from simulation. So, for example, here the amplitude we get from a photo multiplier, or the pure time without calibration should not be displayed. And yeah, and we should keep that in mind when we have a look with it with KM3IO. But first, I just want to prove that the access of the data is possible. So I have here a very, very short example. So when I go in the file just with uproot, then I can read the events, browse to the channel ID, and print out the information. Oh, I see. I think I messed here something up, but I will. Oh, that confuses me. Okay, I think maybe we can talk about this at the end. From the KM3IO perspective, then I already told about this naming we internally have. I take such an offline file reader, and then I can also access the fields. And when I then print out the fields, then you see that these fields I've talked about 2 slides ago, like the amplitude or the pure amplitude, is not given here because it's from a simulation file. And then again here I can access the data as I told, as I did it also for uproot, or I tried to. Yeah. From that on, we have access to the data. I also want to talk about KM3 pipe in order to process the data in a way. So KM3Py is a multi-purpose framework based on the pipe project, and as the name says, this is focuses on pipeline workflow. So the all interoperability functions to all relevant detector interfaces or information are provided by utilizing also other KM3Py packages like KM3IO. So we can use their detector data in the formats we have. And also we can use their directly DIQ, the DIQ network interface to process live data from the detector or also from the database. Inside the package, we also, or the package is able to convert data to HDF5 So we can convert here from different file formats, and this makes it also possible to read it easier from other platforms where you don't have root access, for example. We also have benchmarking there, and we have functionalities for high performance computing. So we directly can submit our scripts to, for example, the talk interface for batch processing. And we have a built-in provenance tracking. So going again to an example for that. So this is basically all you have to do to set up a pipeline. So you create a pipeline instance, and then you attach the modules you want to use. So in this case, I start with an event pump for reading the event files. I've added a status bar to get some feedback of the status of the processing, a calibration of the data, and then I have two custom modules. I will show them on next slide. And then in the end, this all is written out by an HDF5 sync to an HDF5 file. So I've taken two custom modules there because you have in principle two possibilities to work with the data or process the data with your modules. So if you don't need an internal state, you can just pass there and function, which I have here. So you get then from the pipeline one blob where the data is in, and you can access this data, can do your operation. In principle, you can also then store data in the blob to then, for example, store it in the HDF5 file in the end, and then afterwards to send the data to the next module, you return the blob. If you need an inner state, then you can also do it by a class, which is derived from this KM3pipe module. And here you have at the beginning this configure method, and in the end the finish. And for the actual processing, you have this process which is then is then equal to doing it by a function, just with the advantage that you have access to the inner state of your class. So in the end, you have to run this all. So you just do a pipe drain, and then the data is so the pipeline is then executed, and you see here the output of the function for how many hits are in the single event, and for the for this event or for this hit statistics module, here you get the mean number. Okay, that was something on the workflow, but we also do simulation in the with Python, and there I want to give you an overview about. Oh, I forgot the provenance tracking. Sorry for that. You can in KM3pipe, you can also get easily access to all the information of how your data was created by access this provenance field. And this contains all versions of modules or packages you used in there, and this is then printed out here. I have you can access this as in multiple formats. I selected here JSON, and now we come to a simulation package, which is called KM3boo. So for simulating neutrino events, you have to use or reuse neutrino generators, and Gibo is one of them. And the overview about Gibo, it has an factorized model. So the primary interaction is done via neutrino interaction, and the nucleus is modeled as via a relativistic Fermi gas with SUSA potentials. And the final state interactions are done via propagating of phase-based densities using the Boltzmann-Uhling-Uhlenbeck equation. And the problem with that, the Gibo itself is written in Fortran, and we were in contact with the Gibo group to check out how we can utilize this package for KM3net, and it turned out that it's very difficult not to use it in their idea of the workflow. So you have to use it as this monolithic application with the data right out to files, and then you have to convert the files. So in order to do this, this is a Python-based wrapper, which uses then Gibo inside of a container, which we distribute by the KM3 in the Docker container. And with KM3bo, the conversion from the bare neutrino interaction is done to the KM3net data format. So how is this done? So first, you have to set up a neutrino job card, which is basically the Gibo workflow. And here you generate this job card by the basic information about the energy, what target, what interaction type, what flavor. And then you just call this run job card and give it a directory where the data should be written to. And if that has finished, then you can just by this Gibo output object, which is provided by KM3bo, you can parse this data. And for example, if you just want to really use just the Gibo data without any detector specifics, then you can just return it, for example, as a pandas data frame and access the information in there. Or to get really the simulation file, in this case a KM3net specific simulation file. Here I have a single method which writes out this or which converts this data to an KM3net file. And when you just have to provide a few informations there. So basically this Gibo output object and the geometry of the volume where the interaction should be placed. So we have the detector, and then basically can volume around it where the interaction can take place. And in the end, there's also in KM3bo proposal. The proposal package is utilized to propagate tau leptons and to decay them. So when we now use this function, then you can see, okay, you can the example see here. And then we can just, again, use KM3IO to read this data, and you see that this is then a normal KM3net file, which then can be used for further processing in our simulation chain. So, okay. Last project I want to give you an example, or want to show you here, is the KM3 services package. And this is this provides a microservices API for different functionalities, or for example, for calculating oscillation probabilities. Here on the right, you can see how this all works. We have this, the communication is done via REST API in JSON format, and the whole microservice is then running in a Docker container, converting the information from the REST API to NumPy arrays, and then calling the specific library, in this case OSPROP for neutrino oscillation probabilities. This Docker container with this services can run locally. It can run on your own server, or it can be run on our server. So this is very flexible there. And here you have an example how the application works. So in this case, for oscillation probabilities, we set up this oscillation probability object. We give the basic information, so the number of bins, or in this case then energies, the cosine angle from the detector point of view, and then the PDG IDs of the neutrino types. And then we just call here oscillation probabilities for, in this case, the transition from electron neutrinos to all to the other types. And then you see here that this is the expected result for the oscillation probabilities. Yes, so here is an overview about the packages I had not the time to tell you more about. So we have also packages for the for accessing our Oracle database, which stores basically all information about detector hardware, calibration, monitoring, etc. We also have for KM3 flux for parsing flux tables, also with interpolation functionality. KM3 Astro is an extension for AstroPy for coordinate transfer or celestial coordinate transformations with focus on the detector position. This package I've already used in the code. We have there in KM3 test data. We have a collection of all kinds of data formats we use for unit testing, for example. And Rainbow Alga, we have there also an GUI for animating events in the and the light distribution in the detector. So with that, I come to my summary. So the KM3 Pi collection provides high compatibility with all interfaces of the detector. So the challenge I've mentioned at the beginning of the obstacles for reducing the obstacles to access the data, I think for Python we have taken this, or we have solved this. The focus here is on data monitoring, pipelines, and provenance, and also with the aspect that we had from the beginning, the PyRoot bindings, and then now we have this large collection, and this all is widely used in tools and scripts in KM3net, and most of the packages are open source and distributed via PyPy. And as I saw that there's tomorrow also a session on Julia, in KM3net we are also working on Julia packages. So we have already in KM3net an existing framework called NERCA.jl. We have there a real-time event reconstruction for high-level detector monitoring, which is then used in the KM3 Mon, also our monitoring tool we use. And there are also general high-energy physics Julia projects, which originate from KM3 members. So, for example, Unroot, which should provide or provides native root file reading. It's at a very early stage, not with so much features as Uproot, but we're on the way. And Corpuscles is a particle property lookup and PDG-ID lookup package. And for neutrino oscillation probabilities, we have Neutrino.jl. And with that, I would say thank you for your attention.
Thank you very much, Johannes. Very nice, very complete overview. And you have quite a few, well, a good handful of questions coming through on Slido. Are you able to share?
Yeah, I think I've shared my whole screen. So I think, can you see my browser now?
Perfect. Yeah, see that well.
So where we start? I think I start from the bottom because they have prepared something. The monitoring system is pure Python with a little bit of Julia, and I can show you something there. Here I have the our monitoring page, and it's a little bit small. Here you can see this Julia event reconstruction. So that's not publicly available because that's all preliminary data. So I just show it here. But here you can see this live interaction, or we have also for monitoring to see what the status of the detector is. We have here all the triggering. And as I said, all Python with a little bit of Julia. So I hope this is okay. Okay. How do you package and deploy all different pieces of KM3net specific code? I don't know. We have all this specific code. We have the Docker CI. We have most of them, as I said, on distributed via PyPy. So basically, if you are working on this, you can just do a pip install. So we have also our publicly available GitHub profile, and the link you can find in the on the agenda. I added it to to my contribution, so maybe you want to check it out. And I hope this answers the question. To Jim, yes, the Julia session tomorrow, I already planned to be there, so I don't want to miss it. Do you have a sense for how newcomers find has it changed as you use Python more? How to answer that? So I think for this wider range, I think that's better for newcomers, because actually what you can do with C++ or Python, I think that's it's with Python it's an easier start than with root, but I think it basically comes to what you're familiar with. So if you're basically an expert on C++, and as I said in the beginning, we had at the early stage already this Python binding. So I think from my point of view, I maybe don't have the experience now, the overview. I think I cannot answer this, but in general, I think it's more easy with this all Python possibilities. How much interaction is there with KM3net software development and other similar experiments, example ICE group? I'm not really too familiar with the whole software in IceCube. So we have considered using IceTray, but I'm not really sure about now. So we're basically using now our own software. So what time is it? Do we have any others?
You have a minute or two if there's anything you want to highlight that you haven't you think that you missed.
No, I think that's okay from my side.
Okay, well, thank you very much, Johannes, and thanks for handling all the questions. We'll copy those over to Slack, and so again, if you'd be happy to maybe summarize or extend what you said there, that'd be fantastic. So that's also there for others that haven't joined us.
Okay, thanks for having me.
Thank you very much, and thank you for the great talk. And so we move on to our last talk of the session. We have Davide. Let me just make sure you can unmute. There you go. You should be able to unmute now. Who is going to talk to us a bit about quantum machine learning, which is our first and only talk on quantum machine learning, which is probably, well, I'll come back to him. But Davide, do you want to take it away? I'll tell you when you've had 20 minutes.
Okay, great. First of all, can you hear me?
Yep, loud and clear.
Yeah, great. So now you should also see my screen, I hope.
Yeah, we see that.
Okay, great. So let's start. Okay. So first of all, let me thank you, the organizers, for giving us the opportunity to present our work, which is entitled Quantum Machine Learning for Jet Tagging at ACB. So it's gonna be me, Davide, and my colleague, another Davide, and we're going to present this work. So this is a brief outline of our, let's say, presentation. So I will present a physics introduction. So for the physics cases studied at the ACB and our quantum approach. And then I will leave the floor to Davide to give you a brief look at the code. So, as you may know, jet flavor identification is mandatory for several physics cases. So, for example, just to quote two of them that are really, really important for our studies, we have the BB bar charge asymmetry, which is interesting for new physics searches, which is, for example, the physics case that we are going to study in our exercise. So you see here we have the definition of the BB bar charge asymmetry. And basically, there could be some contributions for coming from new physics processes that could, let's say, alter this this value. And another interesting topic is the identification of Higgs boson decay into, for example, BB bar jets, which has been recently observed at ATLAS and CMS, and most importantly, CC bar jets, which has not yet been observed. So basically, final states which are detected by the experiment are jets. And at LHC, but basically at every collider experiment, is fundamental to identify the flavor of the quark, which is originating the jet. And this has been called jet tagging. Let me remind you what the jet is. Well, a jet is just a streams of particles which has been produced by QCD processes in proton-proton collision. So here, for example, you have a sketch where you have your proton collision, then you have the so-called showering process, and then you have the ionization, so the energy deposition in the calorimeters. And particularly at LHCb, for example, we are interested in studying the flavor of the quark generating the jets, and particularly if these jets come from B or B bar quarks. So this technique, of course, is called B-jet tagging. There are two possible approaches, actually, to achieve this task, the so-called exclusive and inclusive algorithms. As you can see from the sketch here, on the top, we have an exclusive algorithm, which is an algorithm that uses the information from a specific process to infer the quark flavor. The one used so far at LHCb is the so-called muon tagging. So basically, you're searching for a muon coming from a B or B bar, since the B or B bar decays semi-electronically with a branching ratio of 10%. And by spotting this muon, you're basically tagging the jet, since the muon and the B quark charges are correlated. A new approach is the inclusive one. So you're not just using information coming from a particle or from a specific physics process, but you're just using the whole information coming from the jet structure. And as you may understand, this is something that can be handled by machine learning algorithms such as deep neural networks. We present briefly the dataset here. We are using the official ACB simulation. So we are simulating dye jets generated by B and B quarks at the center of center of mass energy of 13 TeV. So we're on two conditions. So we have around 700,000 jets, 60% for training and the remaining for testing and evaluation. And what we do is for each jet, we consider 5 types of particles, so muon, electrons, pions, kaons, and protons. And for each of these kind of particles, we select 3 variables. So we select the transfer momentum relative to the jet axis, the distance for each of these particles relative to the jet axis, and the charge of the particle. So we have a total of 15 features coming from these particles. And then we have a global feature, a global variable, yes, which is the total jet charge weighted for the transfer momentum of each particle. So in total, we are using 16 input variables. And let me stress the fact that this is an official ACB simulation, which actually totally resembles real LHCb data. So let's see what has been the quantum approach that we used to handle this problem. So going to quantum, as you may have understood, this is just a classification problem. We have to classify jets coming from B or B bar quarks. So since this is a classification problem, let's say quantum tool that can be used is a so-called variational quantum classifier. Here you have a sketch of structure. So we start with the state preparation. So you have your data and you prepare your data in a specific way. We can say that you prepare a quantum state. These data are then fed into a variational quantum circuit, which has this structure here. As you will see, we can have several geometries, several structures for a quantum circuit. And what you do at the end of the quantum circuit is just measuring the so-called qubits. Okay, so you are going to measure qubits and mapping those measurements to a probability for a jet to be generated from a B or a B bar quark. Once you have found this probability, you, let's say, exit from the quantum side, you go to the classical side where of course you have your output, you compute your cost function, and then you go through an optimization process. So in principle, you have a quantum version of a deep neural network. So you have your data, you fed this data into an algorithm, which has some weights that can be optimized, and you take an output from this classifier. So what we measure, well, basically, as I said, we can measure qubits. To be more precisely, we measure the Z component, and so this, as it is related, let's say, to the Z component of the spin of our qubit, has values from -1 to 1. And coming from this measurement, we define a probability, okay, to be for a jet to be generated by a B or a B bar quark in this way, so that let's say if the maximum probability for a jet to be generated by a B quark is peaked at 1, and vice versa at 0 for a B bar quark. You can use several cost functions, so that, let's say, the most famous one are the mean square error or the cross entropy. And of course, going to the classical optimization side, you have different optimizers, which could be both gradient-free as Cobila or SPSA, or gradient descent optimizers such as ADAM, for example. Concerning the libraries, our exercise has been made using the PennyLane library, which is a rather interesting and, I would say, quite simple interface for doing quantum machine learning using quantum circuit. So first of all, here we were just listing some pros. You have an interface to multiple quantum simulators and hardware. So for example, AWS, which is a service given by Amazon, IBM, Google, or Rigetti, just to quote some of them. You can also do, let's say, pure quantum machine learning, but also the so-called hybrid quantum machine learning. So you can combine both classical and quantum classifiers in a hybrid structure. And the most interesting, let's say, pro is the fact that you have native interfaces to machine learning libraries such as Autograd, PyTorch, and TensorFlow. So I would say this is rather simple in a way. Let me show you some training results. So here we show some training performances. So on the sketch here, on the graph here on the left, you see a possible output of our classifier. So you see this is the probability distribution, okay, for several number of events. And you see indeed that for the B jets, the distribution is going toward the right, okay, is peaked around 0.8. while for the B bar jet is peaked around 0.2. So you see that by dividing into this graph, you have this kind of separation between the two classes. So in principle, you can put some cuts in this probability distribution and perform somehow a discrimination between these two classes. And you can see this by the GIF here on the right, where you have the variation through the epochs, and you see that indeed going through the epochs, so you have this kind of separation of the two distribution. And indeed, you see that the two, let's say, most important figure of merit in this contest, so the loss function and the accuracy, have this kind of behavior. So the loss is actually going down, while the accuracy is actually going up. So this was just a brief overview of this exercise. So now I will leave the floor to my colleague, and we will have a look at the code, which you can find here in our repository. Please.
Hello, good evening. I'm Davide Nicotra, and I will now show the code that we use to perform this analysis. So we have prepared a GitHub repo with a binder section, so that if you want to join us in the analysis in the notebook, you can. I also invite you to do so. And now let me go to the actual notebook. Oops. Seems that the binder has gone down, so let's try to start it again. I'll begin my, oh, it's ready. Okay, nice. So here we are. Let me briefly rerun the notebook so that we have a simple training phase in the notebook, so we will proceed while I talk. So the code is very simple. As my colleague said, the first step is importing the data set. So to do so, we use the pandas, the Python libraries. And in these lines of code, we simply import two CSV files. One contains the train data and one contains the test data. The two, we found it to be suitable for our workflow to pre-divide the data set in the training set and a testing set from the beginning. And here you have the variables. The first list also contains global variables that are used for the analysis, but the actual variables that are fed into the quantum classifier are the 16 that was mentioned by my colleague. So you have 3 variables for each particle, plus a global variables, which is the jet total charge. And finally, the jet level is the ground truth of our classifier, which is the Monte Carlo truth of being a B bar jet or a B jet. So here we have the train data set. So we have the 16 variables and the ground truth. The data undergoes a preprocessing phase before the training process, and to do so, we use a standard scaler combined with an arctangent function. This is the technique that suited well with our QML application. This is mainly due to the fact that quantum gates are parameterized by angles. So this is the main reason of using an arctangent for for the preprocessing. So the all the variables are scaled to have an average of 1 and a standard deviation, an average of 0 and a standard deviation of 1, and then they are passed through an arctangent function in these lines of code. So you can see that post processes data, and then we can build our model, our QML model, using the PennyLane libraries. In this simple example, we use 4 qubits to embed the 16 variables. And this is a sketch of the quantum circuit that we use. We have a first section of the circuit, which is responsible of encoding the 16 classical variables into a quantum states. And this is done by means of an amplitude encoding technique. And then we have the actual trainable part of the circuit, which is these strongly entangled layers. You can put multiple layers of these types one after another, and you can tune by a training process the parameters that are inside these blocks. What are these gates? These are simply rotational gates of qubits parameterized by 3 angles each one. Together with entangling gates, in this case, controlled knot gates, which are responsible for entangling the quantum states. Finally, you perform the measurement of the first qubit, and you map the outcome of the measurement to a prediction for a level of the jet. In practice, we have this code. You firstly import the PennyLane libraries. And then here you can actually tweak your circuit. In this case, we will use a 4-qubit circuit and a total number of layers of 4. I refer to these strongly entangled layers. So the complexity of our circuit can be increased by, for example, enlarging the number of trainable layers. Then the PennyLane libraries requires you to define a device that will execute the circuit. That can be a simulator, which is our case, but could also be a real device, since PennyLane provides interface with real quantum hardware through, for example, Amazon Bracket, AWS Bracket system. The actual quantum circuit is built by means of this decorator, QMLQ node, and the code is really simple and straightforward, as you can see. You define on which device you want to execute your circuit, in our case, the DAV device, so our default.qubit, which is the name of the device. And you also define the differentiation method of your circuit. One main pros of the PennyLane libraries is that it is able to perform the automatic differentiation of the quantum circuit, allowing you to use gradient descent method for the optimization. In our case, we use the backpropagation method for the differentiation, which is suitable for a TensorFlow optimizer, as you will see. So the circuit is defined as a normal function with inputs, which are the variables of the events, and weights, which are the trainable parameters. Here you define the amplitude embedding. So you have this template which automatically performs the embedding, and you pass the input variables and the qubits on which you want to apply the embedding. Then you apply the strongly entangling layers with your trainable weights parameter. And finally, the function returns the measurement, which is the expectation value of the Pauli Z observable on the first qubit. Then you build a model, a Keras model. Another great advantage of the PennyLane libraries is that you can embed your quantum circuit inside a possibly larger model built on top of the Keras framework. As you can see here, we import the Keras framework. we define a quantum layer through this function, which takes in input the circuit, the quantum circuit, and the shapes of the trainable parameters, and gives out the output a Keras layers, which you can use in, for example, a sequential network. Like in this case, we put in series our quantum layer with an activation function, in this case, the sigmoid. And finally, you perform the training. The training is performed by initializing an optimizer, compiling your model, and defining the characteristic of the training data set. In this case, we use a reduced data set due to timing constraints. And once the training is performed, here you can see the performance of the training on the training dataset and on the validation dataset. Here the loss is a mean square error, and we have a very small dataset, so we have very different loss function between training and validation. And this is the accuracy of the model. Then you can perform the testing phase of your model. So here we have a testing data set of 1,000 of events, and we apply the trained model to this data set and take the raw prediction, the prediction of the label of the jet from the quantum classifier. Here you can see a distribution of the probabilities. This distribution is pretty noisy since we have a very small number of events, but you can, in principle, with enough time, you can apply it to the whole data set. And for example, we have here the performance. Also in this case, we have a very bad receive operating characteristic curve since we used a very small training data set. But this can be largely improved by optimizing the model and the size of the training data set. Then you can say,
sorry, Davide, just to let you know, you've had about 20-something minutes. You don't, not to hurry up or rush you, but I mean, just so you're aware. And then also you have a few questions on Slido, which would be great to be able to get to.
Okay, so I'll go straight to the end, and then I'll answer to the question. Okay.
Okay, I think you have. You can keep going a bit, but just be aware.
Okay. Okay. Thank you. So you can save your prediction and performs the actual physics analysis on data, which in our case, in this example, is limited to the evaluation of the performance of the B-tagger in terms of the efficiency of the tagger, of the mistag of the the mistag of the algorithms and the tagging power, which is the main metric for tagging algorithms. And going a bit faster, here you can see the actual plot of the tagging power of this simple classifier with respect to the transverse momentum of the jet. Here you can see the efficiency, which is 100%. You have to interpret this as every event can get a prediction since we have an inclusive model. And this is the mistag, which is quite high since we have a small data set for training and a very simple model in this case. But you can tinker with this simple notebook and actually obtain good results from this data set for this task. Finally, you can, as I said, explore different geometries and tinker with the circuit, tinker with the models and with the data set, and try to build your classifier based on quantum circuits. So let me now take a look at some questions. So can your algorithms be adopted by other experiments like ELIS and CMS? I would say yes. There is nothing in principle going to avoid this. This is actually a very simple model, a very basic model. We have 16 variables that we embed in 4 qubits, but you can have any type of 16 variables, any type of variables, and embed it to your quantum state and perform quantum machine learning. So I would say absolutely yes, you can use it for LSNCMS data. Are you really PID electron muons rather than giving a probability of one with respect to another? I'm not understanding probably the question in this case.
I can answer that. Yes, in principle, LHCb has the ability to PID electrons and muons. Of course, the LHCb algorithm uses the probability for a specific particle to be an electron or muon. Then once you have analyzed all these probabilities, you just give a PID to each particle. So yes, in principle, we are using the PID as let's say as given by the experiment, coming from experimental information. So yeah.
So I see how much the quantum layers improves the results compared to purely classical layer. Yes, maybe we can show.
We can show. Yeah, we also here at the end of the presentation we have let's say what we call some more interesting results. So we have here tagging powers computed with different algorithms. So indeed, for example, you see at the bottom, the red one is the so-called muon tagging. So this, we would say the standard used so far at LHCb, as I said, exploiting the muon charge to infer the beat charge. While on the top you see some classical algorithms, which are basically deep neural networks, LSTMs, so basic classical algorithms. And here you see some performances on quantum algorithms with different geometries. So indeed, we are performing slightly worse in a way. But I think these were not using the same, for example, input variables as the classical ones. We were using a lot of less events with respect to the classical algorithms. So we think that still there is some room for improvement. So we are performing slightly worse, but indeed we must say that we weren't expecting even that. So yeah, it's still nice results from our perspective. Okay, so, okay.
Tagging can distinguish jet and how can I?
Well, in principle, I can answer that.
Yeah.
Well, in principle, yes. Since, as I said, the B tagging at LHCb is performed by means of using the muon charge. So you're just relating the muon charge to the B charge, and therefore you can infer the flavor of the quark, basically generating the jet. The main point here is that by doing so, of course, you lose a lot of events due to the low branching ratio of the semi-leptonic decay of the quark. So the point here is to have a more inclusive approach and in order to lose less events. But yeah, in principle, this is I think this is one of the strong points of LHCb for heavy flavor physics.
Yeah, sorry, let me stress another thing regarding the possible, I would say, quantum advantage under a lot of brackets. The reason why we would like to proceed with the study of quantum machine learning is because due to its intrinsic characteristics, it can allow us to study the jet substructure, possibly looking for correlations between particles inside the jet. This is a peculiar property of quantum machine learning, which we are trying to exploit in doing this. So we are not interested only in performance in tagging, but also in the possibility of studying the correlations inside the jet. So I don't know if this gives some perspective. Is the number of qubits in current hardware a limitation for your case? Yeah, here the answer is very complex. I try to give you a brief overview. At the present stage, we mainly run our code only on simulator. Are the simulators limited by computational constraint? Yes. Simulating quantum hardware is really difficult to do, since the complexity of a problem grows exponentially with the number of qubits. This is the reason why we proposed you a very simple exercise with 4 qubits. Running on real hardware at the moment is tricky also for other reasons. The real quantum hardware have a very long access time, which are not properly compatible with quantum machine learning, with machine learning in general, which requires a lot of evaluation of your function, of your model. In this case, you would have an evaluation for each event during the training, and this is too much expensive for the current quantum hardware.
Yeah, Davide, I'm gonna jump in at this point because I think we've reached our time, but you've still got a few more questions, so we'll definitely copy all of these onto Slack. And I think I may have cut you off there, Davide, so I'm sorry for that, but it'd be great if you can chuck that answer into as well.
No problem.
But thank you very much for a very interesting talk. It's pretty cool to see quantum algorithms being developed for experiments like this. And it's also a good opportunity to highlight that on October 6th, we've got a topical meeting within PyHEP on a quantum computing algorithm package. So please join that. Well, Davide, but everyone else on the call.
Sure, indeed. Sure.
Thank you.
Thank you.
Thank you.
Thank you. So that brings us to the end of today, the 4th day of PyHEP. We've got one more day tomorrow. We will be doing something of a collaboration photo tomorrow, but it will probably be we won't be using Zoom or in a screenshot. We're going to probably send around a form and where we can all upload photos. So we're going to try and do it in a different way to support people that are not connecting on Zoom or joining later on at different times that suits them. So we'll send that out on the announcements channel on Slack. Thank you everyone that's talked today. Thank you everyone that's joined in and asked questions. And we'll see you again tomorrow.